In the beginning, there was darkness. Space and time themselves were yet to exist. Then, in a single instant, an event of unimaginable brilliance set everything into motion. The universe was born in a hot, dense flash about 13.8 billion years ago. All that we know today, every galaxy, star, and planet, was once compressed into a point smaller than an atom. In that primordial moment, the cosmos bloomed from nothingness, and time itself began. In the first fractions of a second, the infant universe expanded at a staggering rate. In a blink, far shorter than a heartbeat, it swelled from microscopic to astronomic scales, a burst of growth known as cosmic inflation. Space itself stretched faster than the speed of light, smoothing the young universe like ironed fabric. Tiny quantum fluctuations, minuscule ripples of density, were stretched vast across the cosmos. These subtle irregularities would, eons later, become the seeds of galaxies and clusters. The newborn universe was an ocean of energy, blazing hot and brilliant. Temperatures soared so high that the known laws of physics teetered at their limits. Matter as we know it could not yet hold together. But as the expansion continued, the fireball began to cool. Within the first second, the temperature fell from trillions of degrees to merely billions. Fundamental forces separated into distinct identities, and a flurry of particle creation began. Matter and antimatter appeared in pairs, only to annihilate in bursts of pure light when they met. It was a cosmic dance of creation and destruction. Out of this fury emerged a tiny imbalance, a crucial miracle. For reasons still mysterious, matter ever so slightly outnumbered antimatter. Perhaps on the order of one particle in a billion, matter gained the edge. When the rest annihilated into energy, that tiny surplus remained. Every atom, every star, every living being owes its existence to that 1 in a billion excess of matter that survived the initial inferno. The universe, still less than a heartbeat old, was a roiling plasma of fundamental particles. Quarks, the building blocks of atomic nuclei, floated freely in a hot soup along with electrons and ghostly neutrinos. In mere microseconds, quarks bound together into protons and neutrons. By the time the universe was a few minutes old, it had cooled enough for these protons and neutrons to fuse. In this brief epoch of primordial alchemy, the first atomic nuclei formed. Most of these new nuclei were simple: hydrogen nuclei, single protons, and helium nuclei, 2 protons and 2 neutrons. By the end of the universe's first 3 minutes, roughly 3/4 of its mass was hydrogen and 1/4 helium. A trace of lithium also emerged. No heavier elements could form under those early conditions. Those would be forged much later, in the hearts of stars yet to be born. Still, the young universe remained blindingly hot and dense. Any atoms that tried to form were ripped apart by the intense radiation. For hundreds of thousands of years, matter and light were inseparable in an opaque glow. Imagine an immense fog of charged particles, a plasma filling all of space, constantly scattering light. Photons, the particles of light, could travel no more than a tiny step before colliding with an electron and veering off in a new direction. The cosmos was brilliant, but nothing could yet be seen through this brilliant haze. As time marched on, expansion cooled the fireball further. When the universe reached about 380,000 years of age, a critical change took place. The temperature dropped to around 3,000 degrees, cool enough for electrons to settle down with nuclei. At last, protons captured electrons to form the first neutral atoms. Suddenly, the fog lifted. Space, once a glowing soup, turned transparent. The trapped light burst free and streamed across the cosmos. This was literally the first light that could travel unimpeded, the grand unveiling of the young universe. Today, we can still detect that ancient light. After nearly 14 billion years of journeying through expanding space, it has cooled and faded to a whisper, the cosmic microwave background. If our eyes could see microwave radiation, the entire sky would glow with a faint afterglow of the Big Bang. It is a soothing, uniform glow, now just a few degrees above absolute zero. But it is not perfectly uniform. Imprinted in this primordial light are tiny variations, slight warmth and coolness, only one part in 100,000 different from place to place. Those tiny ripples are the fingerprints of the early density fluctuations, the seeds from which all future cosmic structure would grow. With the release of the cosmic background light, the universe entered a new phase. The brilliant glow of the beginning gradually dimmed as it stretched into longer wavelengths. The once blinding cosmos grew dark. For a long age afterward, there were no stars at all, nothing to rekindle the cosmic lights. This era is often called the Cosmic Dark Ages, a time of vast darkness, with oceans of hydrogen gas filling expanding space, and the embers of the Big Bang's afterglow fading into the background. Yet even in this darkness, gravity was at work. Those faint irregularities in the primordial matter, slightly denser patches of gas, began to pull surrounding material inward. Over tens and hundreds of millions of years, invisible hands gently squeezed the cosmic gas in some regions, piling matter into ever tighter clumps. The stage was set for a dramatic transformation. The deep night of the cosmic dark ages would eventually give way to a new dawn, the moment when the very first stars set the universe alight. Across the vast expanse, after ages of darkness, a few faint glimmers began to appear. Gravity had been gathering cold hydrogen gas into dense pockets, and around 100 million years after the Big Bang, those clouds reached a tipping point. Deep within one such cloud, pressure and heat built until a new phenomenon burst forth: nuclear fusion. A star, the very first of its kind, flickered into existence. Soon, across the young universe, countless others followed. The cosmic dark ages were ending as pinpricks of starlight punctuated the black void. The first stars had arrived, heralding the universe's long-awaited dawn. These pioneer stars were unlike any that shine today. Born from pristine hydrogen and helium, they had no heavier elements, like carbon or oxygen, to cool their gas, so they grew to monstrous sizes. Many were dozens or even hundreds of times more massive than our sun. They blazed with a ferocious blue-white light, burning their fuel at a relentless pace. In their short lives, just a few million years, a blink in cosmic time, they poured energy into the surrounding gloom. For the first time, starlight travelled through space, illuminating the primeval darkness. The energy from these first stars transformed their surroundings. Intense, ultraviolet radiation flooded outwards, striking the cold hydrogen gas that filled the cosmos. Like a rising sun, burning away morning mist, this radiation began to clear the cosmic fog. It knocked electrons out of neutral hydrogen atoms, turning them back into charged plasma. Gradually, bubble by bubble, the once dark universe became transparent again. This great change, called cosmic reionization, swept across space over hundreds of millions of years. The light of the first stars gnawed holes in the darkness, allowing radiance to spread far and wide. Within the hearts of those early stars, something else remarkable was happening. As they shone, they fused simple elements into heavier ones. Deep inside their blazing cores, hydrogen became helium. Helium fused into carbon, oxygen, and other elements essential for planets and life. But these precious ingredients would not be released until the stars met their explosive end. And that end was not long in coming. Having lived fast and hot, the first stars died in dramatic fashion. When they exhausted their fuel, many erupted as titanic supernovae. In those final blasts, they scattered the first heavy elements into space, seeding the cosmos with the building blocks of future generations of stars and planets. Some of the most massive among them may have collapsed directly into black holes, quietly marking the firstborn of those enigmatic objects. But for the moment, it was the light of their deaths that mattered. Brilliant supernova flashes that briefly outshone entire galaxies, sending shockwaves rolling through the primordial gas. Meanwhile, even as individual stars were living and dying, gravity continued its creative work on a larger scale. The first stars did not shine alone for long. They were born in clusters, and those clusters gathered into the first proto-galaxies. Imagine a small gathering of stars, perhaps only millions of them, bound together by gravity. These were the earliest galaxies, mere seedlings compared to the giant galaxies of today, but galaxies nonetheless. Over time, they merged and grew, drawing in more gas and forming new stars in a gravitational dance. Faint and infantile though they were, these first galaxies began to lace the universe with structure. Clusters of stars merged into larger groups, and small galaxies collided and coalesced into bigger ones. Within a few 100 million years, the cosmos was filled with a tapestry of young galaxies of various shapes and sizes. They burned with youthful vigor, their stars blue and hot, their formations chaotic and new. It is during this epoch that the universe truly blossomed with light on a grand scale, a cosmic sunrise after the long night. Today, our most powerful telescopes are peering back to witness this era. They have spotted tiny, distant galaxies, mere smudges of light, that formed when the universe was only a few % of its current age. These ancient lights, travelling for 13 billion years, tell us that by the time the universe was 500 million years old, it was already brimming with galaxies in their infancy. Each small galaxy in that early time would one day merge, evolve, and perhaps spawn majestic spiral and elliptical galaxies like those we see around us now. Thus, the first stars and first galaxies brought an end to the universe's darkness. The cosmic dawn was in full bloom. What began as isolated sparks grew into the gleam of countless stars grouped in newborn galaxies. The stage was set for all the rich cosmic tapestry to follow. Billions of years of star formation and galaxy growth, leading from those earliest lights to the spectacular universe we inhabit today. As eons passed, the universe's youthful galaxies grew and evolved. Now, billions of years later, we behold a vast cosmic tapestry filled with galaxies of every kind. There are majestic spirals with graceful, pinwheel arms of stars and gas, rotating serenely in space. There are colossal ellipticals, giant swarms of billions of stars shaped like sprawling spheres, relics of ancient mergers. And there are small, irregular galaxies, chaotic in form, often the leftovers of cosmic collisions. Each galaxy shines with the collected light of millions or trillions of stars. Scattered across the cosmos, These galactic islands are the fundamental building blocks of the universe on its grandest scales. Galaxies rarely exist in isolation. Just as stars gather into galaxies, galaxies themselves gather into clusters and superclusters, bound by gravity. In a typical galaxy cluster, dozens or even thousands of galaxies swarm together, orbiting their shared center of mass. For instance, our local group, the cluster containing the Milky Way and Andromeda, is part of the Virgo supercluster, a great assembly of thousands of galaxies. And that in turn is just one lobe of an even larger complex called Laniakea, an immense supercluster of galaxies stretching over 500 million light-years. Such structures hint at the hierarchies of organization in the universe. Our own Milky Way, for example, contains the remains of several smaller galaxies that it has swallowed during its long lifetime. Even now, it is digesting a few dwarf galaxies, and it will pull in others over the next few billion years. If we could step back far enough, we would see that galaxies are arranged in a vast cosmic web. Imagine an immense three-dimensional lattice or sponge. Filaments of galaxies stretch across space, threading together clusters, and between those filaments lie enormous voids, nearly empty of galaxies. This is the large-scale structure of the universe. It is beautiful and strange, a pattern woven over billions of years. The bright threads of the cosmic web are where galaxies and clusters reside, and the dark voids are the spaces in between, some spanning tens of millions of light-years with hardly a galaxy in them. The cosmic web looks almost organic, like the neural network of a giant mind, or the foam of ocean waves frozen in time. What is most astonishing is that this grand structure is only partially illuminated by the stars we see. There is far more matter lurking in galaxies and clusters than meets the eye, an enormous quantity of invisible mass that astronomers call dark matter. This dark matter does not emit or reflect light. We cannot see it directly, yet its gravity betrays its presence. In fact, dark matter makes up the majority of the mass in galaxies and clusters, acting as a hidden scaffold on which the visible universe is built. Without it, galaxies as we know them might never have formed, and those that did would fly apart, unable to hold on to their fast-orbiting stars. Evidence for dark matter first emerged in how galaxies move. Astronomers observed that stars in the outer regions of galaxies orbit surprisingly fast, too fast to be held in place by the gravity of the visible stars and gas alone. Something unseen, providing extra gravitational pull, must surround each galaxy. Similarly, clusters of galaxies were found to contain far more mass than their visible contents account for. The unseen mass binds galaxies together in clusters and bends the light of background objects like a cosmic lens. In one famous example, a massive cluster acts as a gravitational lens and magnifies the galaxies behind it, producing arcs of light in the sky, a visual proof of the hidden mass curving spacetime. Today, we know that dark matter outweighs normal atomic matter by about 5-1. It pervades the cosmos, concentrated around galaxies and in the filaments of the cosmic web. The exact nature of dark matter remains one of the greatest mysteries in science. It could be composed of exotic subatomic particles that flood the universe yet barely interact with ordinary matter. Physicists and astronomers are searching tirelessly for clues, from sensitive underground detectors to powerful particle colliders, hoping to catch a rare interaction or create dark matter particles in the lab. But so far, this elusive substance remains undetected except through its gravity. We find ourselves living in a universe where most of the matter is invisible, a shadow universe overlain on the one we can see. Yet despite its invisibility, dark matter's influence is everywhere. It helped galaxies form by pulling in gas to make new stars, and it keeps galaxies intact. It holds clusters together and traces the outlines of the cosmic web. Without dark matter, the universe would look very different, likely lacking the rich tapestry of galaxies we marvel at. Because of dark matter, the night sky is full of galaxies for our telescopes to explore. In even the tiniest patch of sky, long exposures reveal a multitude of faint galaxies. There are so many that the total number of galaxies in the observable universe is estimated in the hundreds of billions, if not trillions. And each of those galaxies holds billions upon billions of stars. The numbers boggle the mind. The stars in the cosmos likely outnumber all the grains of sand on all the beaches on Earth. This realization, that we live in an almost boundless sea of galaxies and stars, is both humbling and exhilarating. We are part of a massive cosmic ecosystem. Galaxies grow and change over time. They collide and merge, cannibalize smaller neighbors, and spawn new generations of stars. Our Milky Way, for instance, has devoured smaller galaxies in the past and is destined to collide and merge with the Andromeda Galaxy in about 4 billion years. Even on these colossal scales, creation and destruction continue. Amid this cosmic grandeur, it's easy to lose sight of the individual stars that compose these galaxies. But it is within those stars that the universe's most intimate transformations occur. Every galaxy is a glittering collection of stellar stories, stars being born in nurseries of gas and dust, stars living out their lives for millions or billions of years, and stars meeting their end in quiet fades or spectacular explosions. These stellar lives have a profound effect. They forge the elements, light up the galaxies, and sometimes leave behind exotic remnants. To truly appreciate the cosmos, we must now turn to the realm of the stars themselves, the furnaces that power the universe and create its substance. Stars are born in darkness, from clouds of gas and dust that lie scattered between existing stars. Within these cold, colossal clouds, sometimes stretching dozens of light years across, pockets of material occasionally begin to collapse under their own gravity. As they do, they fragment into clumps. Deep inside each clump, the temperature and pressure climb inexorably. In the heart of a contracting cloud, there comes a moment when the crush of gravity ignites a new fire. Hydrogen atoms begin to fuse together, releasing energy. A star is born. Often, many stars form together in a single cloud, like a litter of cosmic siblings. In our own Milky Way, regions such as the Orion Nebula glow with the light of newborn stars, still wrapped in the remnants of the very clouds that gave them life. Hidden within dense, dusty pillars, like the famous Pillars of Creation photographed in the Eagle Nebula, infant stars are sparking into existence, their radiant energy slowly clearing away the cocooning gas. Once a star turns on its nuclear fires, it enters a long, stable adulthood. For most of its life, a star is a self-sustaining fusion reactor, steadily converting hydrogen into helium in its core. The energy released in this process creates an outward pressure that balances the inward pull of gravity. This balance between gravity trying to collapse the star and pressure from the core pushing outward is what keeps the star in an equilibrium. Our Sun, for example, has been in such a stable phase for about 4.6 billion years, and it will continue shining steadily for about 5 billion more. During this time, it fuses hundreds of millions of tons of hydrogen into helium each second, flooding our solar system with light and warmth. Not all stars live the same kind of life. Their fate is primarily determined by their mass, the weight of gas gathered in that initial cloud collapse. Small stars and big stars experience life very differently. The smallest stars, called red dwarfs, contain just a fraction of the Sun's mass. They are cool, dim, and extraordinarily long-lived. A red dwarf sips its nuclear fuel slowly. It can burn for hundreds of billions, or even trillions of years, far longer than the current age of the universe. In fact, not a single red dwarf that formed at the dawn of the cosmos has yet run out of fuel. They will be the last stars shining in the very distant future. By contrast, massive stars live fast and die young. A star with, say, 10 times the Sun's mass burns much hotter and brighter, consuming its fuel at a furious rate. Where our Sun's lifespan is measured in billions of years, a blue-white supergiant might last only a few million. These massive stars blaze tens of thousands of times more brilliantly than the Sun, dominating their local regions of space with their light. As stars exhaust the hydrogen in their cores, the delicate balance that sustained them begins to shift. For a typical star like the Sun, when the core's hydrogen is nearly gone, the core begins to contract under gravity, heating up further. This intense heat ignites a new fusion process in a shell around the core, causing the outer layers of the star to swell dramatically. The star balloons in size and cools at its surface, turning red. Our Sun will undergo this transformation, expanding into a red giant star. In about 5 billion years, it will swell so large that it may engulf Mercury and Venus, and likely render Earth uninhabitable, if not swallow it outright. The Sun's atmosphere will extend far into space, and its colour will shift to a deep orange-red as its surface cools. Many stars go through such a red giant phase near the end of their life, a final regal expansion after a long period of stability. In these bloated giant stars, new kinds of fusion reactions occur in the core and surrounding shells. A star like the Sun will begin fusing helium into carbon and oxygen once the core is hot enough. More massive stars go further. After hydrogen and helium, they fuse carbon into heavier elements, and so on, forging elements like neon, magnesium, silicon, and eventually iron. Layer by layer, the core of a massive star resembles an onion, with different fusion processes in concentric shells. This process of elemental creation is often called stellar alchemy. The stars are cosmic furnaces, transmuting the simple elements of the Big Bang into a rich variety of heavier elements. The calcium in our bones, the oxygen we breathe, the carbon in our DNA. Much of it was manufactured in the nuclear heart of a star during this stage of its life. However, the fusion process has a limit. When it produces iron in the core of a very massive star, the star approaches a crisis. Fusing iron does not release energy. In fact, it consumes energy. So once a core is largely iron, the star can no longer sustain the outward pressure needed to support its weight. At that fateful moment, the life of the star is poised on a knife's edge. The final destiny of a star depends again on its mass. Low-mass stars, those much smaller than the Sun, quietly burn through their fuel and slowly fade out, likely lasting longer than the current age of the universe. A star like our Sun, with intermediate mass, will meet a more dramatic, but still relatively gentle, end. After the red giant phase, the Sun's outer layers will be cast off into space, forming a glowing planetary nebula, a shell of expelled gas expanding away into the interstellar medium. What remains of the Sun will be its core, now exposed, a hot, dense ember about the size of Earth, called a white dwarf. This white dwarf will shine from residual heat, slowly cooling over billions of years, no longer producing energy through fusion. Essentially, the sun's retired core cooling like a dying coal. In time, unimaginable spans of time, the white dwarf will fade to a black dwarf. But the universe is not old enough for any white dwarfs to have cooled that far yet. By contrast, for stars significantly more massive than the sun, the end is far more sudden and cataclysmic. When their cores can no longer generate energy, often after creating iron, they cannot support the enormous weight of their outer layers. In a fraction of a second, gravity wins. The core collapses inwards at nearly 1/2 the speed of light, and temperatures skyrocket. The infalling material rebounds off the hard core, and a powerful shockwave rips outward. The star erupts in a titanic explosion, a supernova, blasting its outer layers into space. For a brief time, this single dying star can outshine an entire galaxy. What's left behind is either a tiny, incredibly dense core, known as a neutron star, or, if the star was truly colossal, the core continues collapsing into a black hole. We will explore these exotic remnants soon. But what's important now is that in those explosive final moments, the star completes its alchemical task. The titanic energies of a supernova forge the heaviest elements, silver, gold, uranium, and hurl them into space along with the star's ashes. These enriched materials mix with the interstellar gas, seeding future generations of stars and planets with the ingredients needed for planets and life. When the largest stars die, they do not go gently. Instead, they end their lives in some of the most spectacular explosions in the universe. These stellar cataclysms, supernovae, are true cosmic fireworks. In the instant of a supernova, a single star's brilliance can rival that of an entire galaxy. The explosion unleashes an enormous amount of energy, sometimes more than our sun will emit over its entire 10 billion year lifetime. For a brief moment, night turns to day around the dying star as it floods its surroundings with intense radiation. Throughout history, humans have occasionally witnessed such celestial blasts. In the year 1054, astronomers in China and elsewhere recorded a mysterious guest star that appeared suddenly in the sky. It was so bright that it was visible in daylight for 23 days, shining 6 times brighter than the planet Venus. That guest star was a supernova, the violent death of a massive star some 6,500 light-years away. Today, we know its remnant as the Crab Nebula, a gorgeous, expanding cloud of debris in the constellation Taurus. At the heart of the Crab Nebula lies a rapidly spinning neutron star, the collapsed core left behind by the explosion. This neutron star, known as the Crab Pulsar, spins about 30 times each second, shooting out beams of radiation like a cosmic lighthouse. Every time its beam sweeps past Earth, we detect a pulse of radio waves and light. It's a stark reminder that what was once a mighty star is now an ultra-dense ember, spinning frantically in the aftermath of its demise. Neutron stars are among the most extreme objects in existence, second only to black holes in their density. Imagine crushing the mass of a star larger than our sun into a sphere only a dozen kilometers across. A neutron star is essentially a giant atomic nucleus, composed mostly of neutrons packed shoulder to shoulder. A sugar cube-sized piece of neutron star would weigh as much as a mountain. In fact, a single teaspoon of neutron star material would tip the scales at billions of tons. The gravity on its surface is so strong that if an object were to fall from a height of 1 meter, it would hit the surface in a microsecond, reaching tremendous speed by the time it impacts. Neutron stars also have intense magnetic fields, far stronger than any magnet or planet. Some neutron stars, called magnetars, boast magnetic fields 1,000,000,000,000 times stronger than Earth's. These magnetic powerhouses occasionally unleash bursts of high-energy radiation when their tangled magnetic fields suddenly realign, creating cosmic flares detectable across the galaxy. One of the most fascinating manifestations of neutron stars is the pulsar, like the one in the Crab Nebula. Pulsars are neutron stars that emit beams of radiation from their magnetic poles. Because these stellar remnants rotate so rapidly, their beams sweep around like the beacon of a rotating lighthouse. To a distant observer, the neutron star appears to pulse on and off. When the first pulsar was discovered in 1967, it baffled astronomers. The signals were so regular that the researchers half-jokingly nicknamed the source LGM for Little Green Men. We now know pulsars are natural, not artificial, but they are no less marvelous. The fastest pulsars spin hundreds of times per second. In fact, the record holder rotates roughly 700 times each second, a mind-boggling speed for an object only about 20 kilometers wide. Pulsars gradually slow down as they lose energy, but many will continue ticking faithfully for millions of years, like cosmic clocks keeping time long after the star that birthed them has vanished. Not every stellar explosion leaves behind a neutron star. Sometimes, if the star is massive enough, even the neutron star core cannot support the fall of all that matter. The core continues to collapse until it forms a black hole, an object with gravity so intense that not even light can escape. We will delve into black holes very soon. But even without a visible remnant, the influence of a supernova persists. The expanding shockwave from the explosion crashes into the surrounding gas of the galaxy, compressing it and triggering the birth of new stars. Supernovae thus sow the seeds of future star formation, even as they announce the death of a star. Supernovae come in different varieties. The type we've described, a core collapse supernova, happens when a massive star reaches the end of its life. But there is another kind, involving smaller stars in binary systems. In these cases, a faint stellar cinder, a white dwarf, the exposed core of a sun-like star, can steal gas from a companion star. If the white dwarf accumulates too much mass, it can erupt in a thermonuclear blast, obliterating itself in an instant. This is called a Type Ia supernova. These detonations always reach a similar peak brightness, making them incredibly useful as standard candles for measuring cosmic distances. In fact, observations of distant Type Ia supernovae led to a shocking discovery. The expansion of the universe is accelerating, but that's a story for later. Beyond supernovae, there are even rarer and more powerful explosions. In distant galaxies, astronomers have detected intense flashes of high-energy gamma rays called gamma-ray bursts. Some of these bursts appear to be linked to exceptionally violent supernova-like events, sometimes dubbed hypernovae, possibly marking the birth of a black hole or the collision of ultra-dense stars. For a few heartbeats, a gamma-ray burst can release more energy than the Sun will emit in its entire existence. If such an event occurred in our galaxy and aimed its energy toward Earth, it would be catastrophic for life. Fortunately, these cosmic blowtorches are exceedingly rare, and none observed so far have been close enough to harm us. Still, they serve as a reminder of the awesome power that the universe can unleash. One particularly important cosmic blast was observed in 2017. Two neutron stars in a distant galaxy had been orbiting each other in a tightening death spiral for eons. At last, they crashed together. The impact was titanic, and for the first time, humanity recorded both the light and the gravitational waves from such a neutron-star merger. The event, called a kilonova, confirmed what scientists had long suspected. Such collisions manufacture heavy elements like gold and platinum in huge quantities. The gold in our jewelry was forged in the cosmic crucible of collisions between dead stars. In the aftermath of the 2017 kilonova, telescopes detected signatures of newly formed gold drifting in the ejecta, a direct testament to the universe's ability to transmute matter in moments of violent upheaval. These cosmic explosions, supernovae, hypernovae, kilonovae, are more than just spectacular light shows. They are the universe's way of redistributing matter and energy, of ending old chapters and beginning new ones. Every supernova enriches the galaxy with elements. Every neutron-star collision shakes the fabric of spacetime itself. They are cosmic engines of change, and they add drama to the universe on a scale that defies imagination, truly fireworks on the grandest stage. Even today, astronomers have their eyes on certain stars that could be future supernovae. One famous example is Betelgeuse, a red supergiant in the constellation Orion. Betelgeuse is nearing the end of its life and could explode any time in the next 100,000 years, a mere blink of an eye in cosmic terms. When it does, it may shine as brightly as the full moon in Earth's sky for weeks, a cosmic spectacle visible even in daytime. Fortunately, at over 600 light-years away, it poses no threat to us. Having witnessed the brilliant death throes of massive stars and the strange new worlds of neutron stars, we now approach perhaps the most mysterious outcome of stellar death. In some cases, gravity's final victory is so absolute that it produces an object utterly beyond our direct observation, a pit in space and time itself. Our journey into these dark cosmic abysses, the black holes, is about to begin. Black holes are the ultimate triumph of gravity, regions where gravity's pull becomes so extreme that not even light can escape. They are, in a sense, holes in the fabric of space-time. A black hole forms when matter is crushed into a tiny volume, usually in the catastrophic collapse of a massive star's core. If the core's mass is above a certain threshold, no known force can halt the collapse. The core shrinks beyond an invisible boundary called the event horizon. Once any object crosses this boundary, it is forever cut off from the rest of the universe. To an outside observer, nothing, no matter, no light, no information, can return from beyond the event horizon. It truly is a one-way door in space-time. Despite this forbidding definition, black holes are not cosmic vacuum cleaners, indiscriminately devouring everything. A black hole still obeys the laws of gravity, much like an ordinary star of the same mass. Planets or stars can orbit a black hole safely from a distance, just as Earth orbits the Sun. Only if an object ventures too close, within the grip of the event horizon, will it inevitably be pulled inward to its doom. What lies inside a black hole, beyond the event horizon? According to Einstein's theory, the collapsing matter continues to compress to an infinitely dense point at the center, known as the singularity. Space and time themselves become severely distorted near this point. At the singularity, our current understanding of physics breaks down. It's a realm that challenges comprehension, a place where the density is infinite, and the very notions of time and space may cease to have meaning. For all their mystery, we have compelling evidence that black holes are real and plentiful. Astronomers have observed stars whipping around an unseen massive object at the center of our Milky Way galaxy. These stars move so fast, thousands of kilometers per second, that only a supermassive black hole, about 4 million times the mass of our Sun, could be tugging on them. In 2019, the world glimpsed the shadow of a black hole for the first time. The Event Horizon Telescope captured an image of the supermassive black hole in galaxy M87, outlining a bright ring of light warped by gravity around a dark center. That dark region was the silhouette of the black hole's event horizon. More recently, a similar shadow was imaged for the black hole at the Milky Way's core. These landmark observations confirmed that black holes are not just theoretical curiosities. They actually exist, and we can observe their impact on surrounding light and matter. When black holes feed, they can become the most luminous objects in the universe. Gas and dust spiraling into a black hole form a superheated accretion disk outside the event horizon. Friction and magnetic fields in the disk make it glow fiercely, emitting X-rays and other high-energy radiation. In the hearts of young galaxies, supermassive black holes gorging on infalling gas become quasars, brilliant beacons visible billions of light-years away. A quasar is essentially a black hole announcing its presence by the ferocity with which it devours matter. The paradox is striking. The darkest objects in the cosmos can produce the brightest lights through the matter they consume. Some of the infalling gas doesn't fall straight in at all. Instead, it is redirected by magnetic forces into twin jets that shoot out from the black hole's poles at nearly light speed, beaming radiation and particles far into space. Such jets have been observed emerging from the centers of distant galaxies, a further testament to the mighty influence of black holes. The environment near a black hole is like nothing else. Tidal forces, the difference in gravity between one side of an object and the other, grow tremendously strong near the event horizon. If an unlucky astronaut fell toward a stellar mass black hole feet first, the gravity at their feet would be far stronger than at their head. This difference would stretch the astronaut out like a noodle while also compressing them sideways. A gruesome effect whimsically termed spaghettification by scientists. For a small black hole, an object would be torn apart even before reaching the event horizon. Around a supermassive black hole, the tidal forces at the horizon might be gentler, allowing an astronaut to slip through unharmed, only to be crushed at the singularity moments later, meeting the same fate. Time itself behaves strangely near a black hole. To a distant observer, an object falling toward the horizon appears to slow down and fade, never quite falling in. In reality, from the infaller's own perspective, they would plunge through the horizon after a finite time, their clock running normally while the universe outside speeds into the future. Black holes also produce some of the most profound phenomena ever detected. Gravitational waves. When two black holes orbit each other and eventually merge, they release energy in the form of ripples in spacetime, waves that stretch and squeeze distances as they pass. In 2015, the LIGO Observatory on Earth directly sensed such waves for the first time, emanating from a merger of two black holes about 1.3 billion light-years away. During the final fraction of a second, the two black holes collided into each other at nearly half the speed of light and formed a single, more massive black hole, converting a portion of their mass to energy, according to Einstein's formula E, mc2. This energy was emitted as a final strong burst of gravitational waves. At its peak, the merger radiated more power in gravitational waves than the light from all the stars in the observable universe. These waves were incredibly subtle by the time they reached Earth, making the mirrors in LIGO's detectors move by less than the width of an atom. Yet that tiny vibration was enough to reveal the cosmic collision. Since then, dozens of black hole mergers have been heard by gravitational wave observatories, opening a new window on the cosmos. We can now listen to the universe in gravitational waves, sensing events utterly invisible to traditional telescopes. As remarkable as black holes are, they might not be truly eternal. Quantum theory predicts that they should very slowly lose mass via Hawking radiation, a faint emission of particles from just outside the event horizon. A black hole the mass of our Sun would take an unimaginable length of time to evaporate, far longer than the current age of the universe. So for all practical purposes, black holes live essentially forever by human standards. Still, the idea that these dark giants could eventually fade away adds another layer of intrigue to their story. Our journey through black holes has shown us the depths of what gravity can do. From the slow dance of stars around an unseen mass, to the violent merger of holes that makes the very fabric of space ring like a bell. Black holes push physics to its limits. Yet, even as we come to understand these enigmas, the universe has more surprises in store. On the largest scales, gravity is not the only force at play. There is another, far more mysterious influence that is driving the universe's evolution. One that operates not to pull things together, but to push the cosmos apart. As we leave the realm of all-consuming gravity, we turn to face the dark energy that is accelerating the expansion of our universe, and consider what this phenomenon might mean for the future and ultimate fate of everything. For decades, astronomers assumed that gravity's pull would gradually slow the expansion of the universe. After all, the collective gravity of all galaxies and matter should be tugging everything inward. Perhaps, given enough time, the expansion might even halt or reverse in a distant future big crunch. But in the late 1990s, a remarkable discovery turned that thinking on its head. Two independent teams observing distant type Ia supernovae, those stellar explosions used as standard candles, found that those supernovae were dimmer and farther away than expected. The universe wasn't slowing down at all. To everyone's astonishment, it was speeding up. The expansion of the cosmos had begun to accelerate. This revelation was so shocking that at first many thought it must be a mistake. Yet observation after observation confirmed it. The universe, already born in a violent expansion, is now, billions of years later, accelerating outward as if pushed by a repulsive force. Cosmologists named whatever is driving this acceleration dark energy. It's dark because we cannot see it or directly detect it, and energy because it appears to be a property of space itself, a sort of latent energy woven into the fabric of the cosmos. Einstein himself had once introduced a similar concept, a cosmological constant, to allow for a static universe in his equations. He later discarded it when cosmic expansion was discovered, reputedly calling it his greatest blunder. Ironically, this same idea of a built-in energy to space may be close to the truth. Dark energy now dominates the universe's energy budget. According to the best measurements, about 68% of the total contents of the universe is this mysterious dark energy. Roughly 27% is dark matter, the unseen mass holding galaxies together. And only about 5% is the ordinary matter that makes up stars, planets, and people. In other words, everything we have discussed so far, all the galaxies and luminous things, are but a small frosting on an enormous, dark, cosmic cake. What could dark energy be? One idea is that it's a built-in property of space. Essentially, Einstein's cosmological constant revived. If so, as the universe grows, new space brings more of this energy, and the repulsive effect doesn't dilute with time. Another possibility is that dark energy is a new kind of field or force, something that permeates the universe, but that we haven't yet identified in the lab. For now, dark energy remains a profound enigma. We see its handiwork, the speeding up of cosmic expansion, but we don't yet understand its source. The influence of dark energy became significant a few billion years ago, once the universe had expanded and thinned out enough for this mysterious pressure to overcome gravity on large scales. Today, it's the dominant factor governing the universe's fate. As space expands faster and faster, galaxies far from us are receding at ever-increasing speeds. In the far future, distant galaxies will slip beyond our observable horizon. Their light will no longer reach us. Tens of billions of years from now, a sky watcher in our galaxy, or its merged descendant after the Milky Way and Andromeda collide, might see nothing beyond the local group of galaxies, all other galaxies having become too faint and too distant to detect. The universe will appear dark and empty to those far future astronomers, as if ours was the only galaxy in existence. Of course, over even longer timescales, stars will age and die. New star formation will cease as gas is used up, and galaxies will go dark one by one. The cosmos will grow cold and quiet, a scenario sometimes called the Big Freeze or heat death of the universe, where all that remains are the fading embers of once brilliant stars and black holes slowly evaporating over inconceivable eons. There is a possibility that dark energy may not remain constant. If the strength of dark energy changes with time, the fate of the universe could look very different. If, for example, dark energy grows stronger in the future, a scenario dubbed the Big Rip, it could eventually overcome all other forces, tearing apart galaxies, stars, and even atoms in a final, catastrophic expansion. In a Big Rip scenario, for example, galaxy clusters would disperse billions of years before the end. Stars and planets would be torn apart perhaps minutes before the final moment, and then even atoms and subatomic particles would be ripped asunder in the last tiny fraction of a second. Alternatively, if dark energy were to weaken or somehow reverse, something not indicated by current observations, the expansion might slow and potentially recollapse, leading to a big crunch or perhaps a rebirth of the cosmos. However, the simplest explanation, and the one most cosmologists currently favor, is that dark energy is a constant property of space. In that case, acceleration will continue forever. Peering far into the future, then, we see an ever sparser cosmos, with island galaxies isolated in a vast, dark gulf. It's a melancholy vision. Yet, in the here and now, we are fortunate to witness the universe in its youthful bloom, rich with galaxies, sparkling with stars, and capable of contemplating itself through conscious beings. The discovery of dark energy reminds us that there is still so much we don't know. We find ourselves living in a universe dominated by something deeply mysterious, and every step we take toward understanding it reveals new questions. Our exploration in this part has carried us from the dawn of time to the far future, from the birth of light to the forces pushing the cosmos apart. It's a grand and humbling narrative. And even as we conclude this chapter of the story, it's clear that the story itself continues. The cosmos still holds countless secrets. For now, we pause on the threshold of further discovery, filled with wonder at how far we've come, and gently anticipating the journey still to come. In the beginning, there was darkness and dust. Over 4.5 billion years ago, in a quiet corner of the Milky Way, a vast cloud of gas and cosmic debris drifted silently. All was cold and still. Then, Something disturbed this delicate cloud, perhaps the distant explosion of a dying star, sending a ripple through the nebula. The cloud began to collapse under its own gravity. Slowly at first, then faster, it spiraled inward, spinning like a whirlpool in space. Pressure and temperature climbed at the center of this maelstrom. Hidden deep in the collapsing cloud, a new light was about to be born. At the heart of the swirling disk, matter clumped tighter and tighter. As atoms squeezed together under crushing gravity, the core of this protostar grew hot, tens of millions of degrees hot. One day, in a moment unimaginable and yet inevitable, nuclear fusion ignited. Hydrogen atoms fused into helium, releasing a tremendous burst of energy. A star blinked on. Our sun had awoken, its brilliant light breaking the primordial darkness. The infant sun blazed with fierce luminosity, illuminating the remaining shroud of dust around it. This was the dawn of our solar system. Within that collapsing cloud were atoms forged in earlier stars, the calcium in our bones, the iron in our blood, cast across the galaxy by ancient supernovae. The birth of our sun was not only a beginning, but also a continuation of cosmic cycles. Encircling the newborn sun was a flattened disk of leftovers, fine grains of dust and wisps of gas, all that remained of the original cloud after the star's birth. Within this spinning disk, tiny particles gently collided and stuck together. Over countless years, dust gathered into pebbles, pebbles into rocks, and rocks into asteroids and boulders. These building blocks danced around the young sun, occasionally colliding violently. Each collision built larger bodies, the embryos of planets. It was a chaotic nursery, with pieces merging, fragmenting, and merging again, all under the sun's warming gaze. In the inner parts of this protoplanetary disk, the sun's heat chased away most of the light gases. Only heavier materials, metals and rocks, could solidify so close to the fierce young star. Thus, the inner worlds forming here would be relatively small and dense. Farther out, beyond an invisible frost line, it was cooler. Here ices could condense and fragile gases like hydrogen could be captured. In these distant orbits, much larger planets swelled, gathering thick blankets of gas around solid cores. As the sun matured, it sent out a powerful solar wind, a stream of charged particles blowing through the new solar system. This gusty stellar wind cleared away much of the remaining gas and dust, especially from the inner regions. The era of planet building drew to a close. What remained were 8 newborn planets circling their parent star, along with countless smaller remnants. The stage was set for an elaborate cosmic family to evolve over billions of years, a star with a retinue of worlds, each unique. In the solar system's turbulent youth, stray debris still littered the sun's kingdom. For hundreds of millions of years, leftover asteroids and comets bombarded the young planets. Each impact gouged out craters and melted landscapes. Mercury, the Moon, and many other airless surfaces were scarred with these pockmarks, enduring records of that violent era. Some impacts may have even delivered water and organic molecules to the young worlds, seeding the ingredients for future oceans and life. Eventually, the chaos settled. The major worlds took up stable paths around the sun. The solar system had reached a semblance of calm, setting the stage for the diverse planets we know today. Our sun, now a steady beacon of light, sits at the center of its family. It holds almost all of the solar system's mass, a giant by far compared to its offspring. Yet despite its dominance, the sun is but an average star in size, one among billions in our galaxy. For us, though, it is the life-giver, the golden heart of our cosmic home. It shines steadily, its surface roiling with hot plasma, as it has for ages. The planets travel around it in silent obedience, bound by invisible threads of gravity and bathed in its radiant warmth. Draw closer to the sun, and you feel its fierce energy growing. Mercury, the closest planet, is little more than a scorched pebble in orbit, subjected to the sun's unyielding glare. Each world farther out will tell a different chapter of this celestial story. From fiery Mercury to distant Neptune, the solar system unfolds like a grand gallery of wonders shaped by the sun's presence. Our journey through this family of worlds begins at the sun's doorstep, where the light is blinding and the heat intense. We will travel outward, moving slowly from the brilliance of the inner solar system toward the cold twilight of its edge, and then beyond. The first world we encounter is Mercury. It is a tiny, broiling ball of rock, the innermost planet of the sun. Mercury is barren and pockmarked, looking much like our moon with its countless craters. Those craters are ancient scars from the era of heavy bombardment, preserved on Mercury's airless surface. The little planet is only slightly larger than Earth's moon, making it the smallest of the 8 planets since Pluto's reclassification. Up close, Mercury's landscape is a study in extremes. Vast, silent plains and steep, wrinkled cliffs that formed when the planet's crust shrank as its interior cooled. Impact craters, large and small, dot the grey terrain, some with bright rays of ejected dust fanning out across the surface. On Mercury, the sun dominates the sky. With no substantial atmosphere to soften the glare, daylight is stark and piercing. From Mercury's surface, the sun would appear more than 3 times larger than it looks from Earth, and about 7 times brighter. At noon, the ground underfoot roasts under this intense sunlight. Surface temperatures can soar above 800 degrees Fahrenheit, hot enough to melt lead. The rocks and dust bake in an oven-like heat. If you were standing on Mercury at midday, you'd see the landscape shimmering, and above you, a pitch-black sky. Without air, there is no soft blue haze, only the stark darkness of space, even while the sun blazes overhead. Yet Mercury also plunges into bitter cold. The planet rotates very slowly. One Mercury day, sunrise to sunrise, lasts a long time. In fact, Mercury spins so sluggishly that a single day-night cycle lasts 176 Earth days, which is 2 Mercury years. During its extended night, with the sun absent for months, the heat radiates away into space, and the ground cools drastically. Temperatures can plummet to nearly 300 degrees before dawn. Mercury experiences the most extreme temperature swings of any planet, from searing day to frigid night, all in the absence of an atmospheric blanket. Mercury lives up to its swift namesake in other ways. It races around the sun faster than any other planet, completing one orbit in just 88 Earth days. In that short year, it hurtles through space at nearly 30 miles per second. But its slow rotation makes the sun's journey across Mercury's sky unusual. Around Mercury's sunrise, if you were in certain areas, you'd see the sun peak above the horizon, then oddly dip down again briefly, and rise once more, an outcome of Mercury's elliptical orbit and sluggish spin. Time and rhythm work differently on this little world so close to the sun. Though Mercury's day side is infernal, there are pockets of eternal shadow at its poles. In deep craters near the north and south poles, the sun's rays never reach the floors. There, in permanent darkness, it is cold enough that water ice can exist. And indeed, scientists have detected bright radar reflections, hinting at ice hidden in those dark craters. It's startling to think that even on the solar system's innermost planet, frost glistens in the shadows, untouched by the sun's fierce heat. Mercury, a world of light and shadow, heat and ice, marks the beginning of our journey outward. As inhospitable as Mercury is, it is not the hottest planet. That title belongs to the next world out from the sun, a planet that, despite being farther away, has transformed into a true hellscape of heat. We leave airless Mercury behind and approach the brilliant white clouds of Venus, where an even more extreme environment awaits. Venus shines like a brilliant pearl in our sky, veiled by thick, reflective clouds. At first glance, it might seem serene. Ancient stargazers called it the morning star, or evening star, admiring its bright, silvery glow. In size and gravity, Venus is Earth's near twin. But beneath its shroud of clouds, Venus hides an inferno. It is a world gone wrong, a cautionary tale of a planet overwhelmed by greenhouse heat. As our spacecraft descends through Venus's upper clouds, the conditions grow more hostile with every mile downward. The atmosphere of Venus is incredibly dense and stifling. Carbon dioxide gas makes up the bulk of it, with clouds of sulfuric acid perpetually swirling. These clouds are so thick and reflective that they hide the surface completely from view, bouncing sunlight back into space, which is why Venus gleams so brightly from afar. But this thick blanket also traps heat. Sunlight filters down and warms the surface, and the heat cannot effectively escape back to space. The result is a runaway greenhouse effect of nightmarish proportions. The surface temperature on Venus hovers around 865 degrees Fahrenheit, about 460 degrees, everywhere, day or night, pole to equator. It is hotter on Venus than on Mercury, even though Venus is nearly twice as far from the Sun. The heat is unrelenting and suffocating. Descending through Venus's atmosphere is like venturing into a pressure cooker. The air pressure at the surface is over 90 times the pressure at Earth's sea level, equivalent to being almost a kilometre beneath the ocean on Earth. The dense air presses on you from all sides. And it's not just hot, it's corrosive. Sulfuric acid droplets ride on high-speed winds in the clouds, a caustic mist whipping around the planet. Lightning flickers within the cloud decks, illuminating the toxic sky with brief, ghostly flashes. High above, hurricane-force winds encircle the planet, but near the ground the air is oppressively still, locked in a perpetual yellowish twilight under the thick cloud cover. A day on Venus is strangely long. The planet turns on its axis extremely slowly, and in the opposite direction of most planets. One Venusian day, one rotation on its axis, takes about 243 Earth days, which is actually longer than Venus's year of 225 Earth days. This backwards rotation means on Venus, the sun would appear to rise in the west and set in the east, though thick clouds would prevent you from ever seeing the sun directly. The concept of day and night loses its meaning when the sun's light barely penetrates the gloom. At the surface, it is perpetually murky and red-tinged. If we could stand on Venus's rocky ground, we'd find ourselves in a dim orange haze with no discernible sun or stars, just an eternal sulphurous overcast. The surface of Venus is a tortured landscape. NASA's radar maps and Soviet landers have revealed a world of volcanoes and plains, crushed and contorted by the planet's own weighty atmosphere. There are vast volcanic lowlands and deformed highlands with ridges and troughs. Much of Venus's surface appears to have been paved over by lava in the planet's relatively recent past, geologically speaking. Impact craters are few and far between because meteoroids burn up in the thick atmosphere before reaching the ground, and because volcanic resurfacing has covered older craters. In fact, scientists suspect that Venus undergoes periodic episodes of global resurfacing, massive outpourings of lava that renew most of the crust. And there may still be active volcanoes today. Data from orbiters and recent studies have hinted at changing thermal hotspots and altered sulfur dioxide levels in the atmosphere, possible signs of ongoing eruptions. If true, Venus is not a dormant world, but one that continues to remake itself in fire. For all its hostility, Venus may not always have been so unlivable. Some research suggests that long ago, billions of years in the past, Venus might have been temperate, with gentle seas and blue skies, more akin to a primeval Earth. If Venus had oceans early on, they eventually evaporated as the sun's energy output increased over time. With water gone, carbon dioxide accumulated unchecked in the atmosphere, and the greenhouse effect spiraled out of control. The planet's history likely went from habitable to horrendously inhospitable as a result. In Venus, we see a possible fate that could have befallen Earth if circumstances had been only slightly different. It's a sobering glimpse of a runaway climate, a warning written across the face of our neighbouring world. No human has ever visited Venus's surface. The environment is too extreme, but a few hardy spacecraft have. The Soviet Venera probes in the 1970s and 1980s parachuted through the clouds and briefly touched down, surviving only minutes to a couple of hours in the searing heat and crushing pressure. They managed to send back our only images from Venus's surface, haunting photos of a dim, rocky plain under a sulphur-coloured sky, with flat, eroded stones stretching to the horizon. The landers showed that the rocks are basaltic, similar to volcanic rocks on Earth, and they confirmed that the air is nearly pure carbon dioxide with traces of nitrogen. Shortly after, the cameras went silent as the probe succumbed to conditions that no electronic device or living thing can long endure. Intriguingly, not everything about Venus is death and fire. High up in the atmosphere, about 30 miles above the surface, the pressure and temperature become surprisingly Earth-like. In those golden cloud layers, one finds relatively mild conditions, around room temperature and a pressure similar to Earth's surface. If one could hover there in a balloon, the environment would be much more tolerable, aside from the acidic chemistry. Some scientists have speculated that microbial life could potentially exist in Venus's upper atmosphere, where droplets and mysterious dark streaks appear that absorb ultraviolet light in an unexplained way. In 2020, astronomers reported the detection of phosphine gas in the clouds of Venus, a gas which, on Earth, is produced mostly by microbial life. The claim was controversial and is still debated, but it sparked new interest in the idea that life, in some form, could persist in Venus's skies, even if the surface is barren. It's a long shot, yet it reminds us that life can be tenacious and might find niches, even in unlikely places. We leave Venus behind, awed by its dazzling brightness and harsh reality. Ahead, our next destination could not be more different. After the suffocating heat and acid clouds of Venus, we arrive at a world of blue oceans, white clouds, and abundant life. A true oasis in space, the planet we call home, Earth. Our spacecraft now comes upon Earth, the third planet from the Sun, our home. Seen from space, Earth is breathtaking. A shimmering blue marble swirled with white clouds, with brown and green continents peeking out from beneath the atmosphere. In stark contrast to the lifeless rocks we've visited so far, Earth teems with life. It is the only planet we know of that is alive in the biological sense, covered in millions of species and ecosystems. A delicate atmosphere surrounds the world, a mix of nitrogen and oxygen that draws a soft blue halo around the planet and nourishes life below. Warmth from the sun, moderated by Earth's just right distance, allows liquid water to exist in abundance. Water covers more than 2/3 of Earth's surface, filling deep oceans that cradle life and regulating the climate. Earth orbits in the so-called Goldilocks zone, not too hot, not too cold, where rivers can flow and rain can fall. In this temperate band, water cycles comfortably through solid, liquid, and vapor phases, driving our weather and sustaining living organisms. From high above, we watch day and night dance across Earth's face. On the day side, sunlight sparkles on the ocean waves and casts soft white highlights on the tops of clouds. We see the verdant greens of forests and the tawny browns of deserts. On the night side, a gentle sprinkle of lights in clustered patterns hints at human cities twinkling below. A clear sign that something clever is afoot on this world. No other planet has revealed such a direct indication of technology. Earth is alive in every sense. Geologically, with shifting tectonic plates that cause continents to drift and clash, building mountains and triggering quakes and volcanoes. And biologically, with a biosphere that has transformed the surface over eons. The air we breathe, rich in oxygen, is itself a product of life, exhaled by countless plants and photosynthetic microbes over billions of years. To an outside observer, Earth's atmosphere would appear distinctly out of chemical balance, too much oxygen, which normally would bond with rocks unless constantly replenished. That imbalance is a fingerprint of life, screaming into the cosmos that something is happening here. Earth's hospitable environment is a product of many fortuitous factors working together. Our planet's size is just right to hold onto an atmosphere, but not so large as to become a gas giant. Earth's rapid rotation, 1 day per 24 hours, and its liquid iron core generate a magnetic field that envelopes the planet, an invisible shield deflecting much of the sun's charged particle radiation. This magnetosphere, along with Earth's ozone layer in the upper atmosphere, protects the surface from harmful radiation that could otherwise strip away our atmosphere and batter living cells with DNA-damaging rays. Meanwhile, Earth's axial tilt of about 23.5 degrees provides mild seasons as the planet orbits the sun. Neither the temperature swings nor the sunlight variations are too extreme. The rhythm of spring, summer, autumn, winter has given many forms of life time to adapt and thrive. One of the most striking features in Earth's sky is its single natural moon. The moon hangs there as a constant companion, influencing our world in subtle but profound ways. Our moon is unusually large relative to Earth, about 1/4 of Earth's diameter, making the Earth-Moon system almost a double planet. Its presence is no coincidence. According to prevailing theory, over 4 billion years ago, a Mars-sized protoplanet collided with the young Earth, blasting out debris that eventually coalesced into the moon. In the aftermath of that titanic impact, Earth's tilt and rotation may have been significantly affected, and the moon initially glowed red-hot, molten from the energy of formation. But as eons passed, it cooled into the grey, cratered body we know. Today, the moon is a silent, airless world, locked in synchronous rotation with Earth, meaning the same side of the moon always faces us. Its surface is covered in dark lava plains, the Maria, and bright, ancient highlands, pitted by innumerable craters from long-ago impacts. Though lifeless, the moon has been a steadfast guardian of Earth's habitability. Its gravitational pull raises the tides in Earth's oceans, a rhythmic ebb and flow that may have been crucial for early life, adapting from sea to land, and that continues to shape coastal ecosystems to this day. The moon's presence also stabilizes Earth's axial wobble. Without the moon, Earth might wobble chaotically over millions of years, leading to wild swings in climate from extreme tilts. With the moon's stabilizing influence, Earth's tilt stays within a moderate range, ensuring relatively stable seasons over geological timescales. This stability has given life a steady environment in which to develop and evolve. In short, the moon has been a calming anchor for Earth's environment. Many nights on Earth, the moon adorns the sky with a gentle glow, sunlight reflected off its dusty surface. For most of human history, it was a distant beacon of wonder and inspiration. Then, in July 1969, humans stepped onto the moon's surface, marking the first time our species set foot on another world. Apollo astronauts gazed back at Earth, rising above the moon's horizon, a fragile blue-white orb suspended in the blackness of space. That iconic Earthrise image changed our perspective forever, showing us our home as a small, precious sphere without borders or divisions. The footprints those astronauts left in the lunar dust remain there even now, undisturbed decades later. With no atmosphere and no weather, the moon's surface changes only slowly. A footprint, or the tracks of a rover, could last millions of years under the unchanging sky, a testament to the moon's stillness. Interestingly, like Mercury, and like some deep craters on Venus, the moon harbours water ice in the permanent shadows of certain craters at its poles. Where the sun never shines, temperatures plunge to extraordinarily low levels, and comets over the ages have deposited ice that persists, frozen in the dark. Recent missions have confirmed that thin frost and patches of ice lie hidden in craters near the lunar poles. This discovery hints that even our barren moon holds resources that could be invaluable for future explorers. Water for drinking, oxygen from its components for breathing, and hydrogen for fuel, all locked up in the regolith, waiting to be utilized. Earth and its moon journey together around the sun, an intimately linked pair. Earth, vibrant and dynamic, and the moon, quiet and unchanging, illustrate the contrasts and connections that make our planetary system so fascinating. As we depart this blue oasis and its grey companion, we carry with us a renewed appreciation for how unique and precious a habitable world is. It also raises a profound question. Is Earth the only cradle of life, or could there be others? To begin exploring that question, we set our sights on the next planet outward, a smaller, colder world that has long fired our imaginations. We venture onward to the red planet, Mars, humanity's next-door neighbour, and a world that beckons with hints of an ancient past that might have included life. Mars, the fourth planet from the Sun, appears in our night sky as a reddish-orange star, steadily wandering against the backdrop of constellations. Named for the Roman god of war, due to its blood-red colour, Mars has long been the subject of speculation and romance. Now, as our spacecraft draws near, that red dot becomes a rusty globe, revealing a desert planet, both familiar and alien. Mars is about half the diameter of Earth, and has a gravity just 38% of Earth's, so walking there would make you feel light and bouncy. Its surface is coated in iron oxide dust, essentially rust, which gives the soil and the sky a light reddish tint. We approach over golden deserts and wide craters. A thin atmosphere hugs the planet, visible as a hazy aura at the horizon. The sunlight here is weaker than on Earth, only about half as intense, casting a butterscotch hue over the barren terrain. Touching down on Mars would bring us to a cold, dry desert. The ground is strewn with rocks and fine dust that clings to everything. Above, the sky during the day is not blue, but a pale yellow-orange, often tinted by dust suspended in the air. If you were to stand on Mars, you'd notice that distant features appear muted and slightly blurred by the thin haze. The horizon might be adorned by the towering cone of Olympus Mons far away, the largest volcano in the solar system, rising roughly 13.6 miles high, 22 kilometers, about 2.5 times Everest's height, but with such a broad base that you might not even realize you're looking at a mountain. Or perhaps you'd see the jagged outline of Valles Marineris if you were near the equator, a canyon system that would stretch from Los Angeles to New York if it were on Earth, so vast and deep that the Grand Canyon would be just a minor branch of it. Despite its barren appearance now, Mars holds a wealth of evidence that it was once a very different world. We see ancient river channels etched into the ground, winding and branching, dry for billions of years now, but unmistakable in their resemblance to riverbeds on Earth. We find enormous outflow channels that suggest catastrophic floods poured forth at some point, carving grooves and teardrop-shaped islands around obstacles. Mars's polar caps, gleaming white when viewed from space, are made of frozen carbon dioxide, dry ice, and water ice layered together. In the Martian winter, they expand as CO2 from the atmosphere freezes onto the surface, and in summer they partially sublimate, sending gas back into the thin air. This seasonal breathing of the polar caps shows Mars still has an active climate, albeit a tenuous one. Long ago, Mars was more Earth-like. That is the picture that's emerging. Roughly 3.5 to 4 billion years ago, Mars is believed to have had liquid water on its surface. Lakes, rivers, perhaps even a northern ocean, covering a third of the planet. It likely had a thicker atmosphere then, and a magnetic field to shield it. But something changed. Mars lost most of its magnetic field, perhaps as its small core cooled, and without that protection, the solar wind stripped much of the atmosphere away. The pressure dropped, water evaporated or froze, and the planet became the cold, arid place we see now. Still, the signs of past water remain everywhere. In the minerals, like clays and hematite, that form in water, detected by rovers. In the sedimentary rock layers that speak of ancient lake beds. In the rounded pebbles that once tumbled in streams. And even in the presence of certain chemicals in the soil that could only be explained by long-term interaction with water. Mars today is a world of extremes in its own subtle way. At the equator during summer midday, temperatures might barely climb above freezing, maybe reaching 50 degrees, 10 degrees, in a sheltered spot, comfortable enough if you were in a spacesuit. But at night, even at the equator, it plunges to 100 degrees, 73 degrees. Near the poles, or in winter, temperatures sink even further, to 150 degrees, 101 degrees, or below. The atmosphere is almost all carbon dioxide, but so thin, about 0.6% of Earth's surface pressure, that it offers little insulation or oxygen. A faint wind may blow, raising dust into devilish whirlwinds called dust devils that dance across the plains, leaving dark streaks in their wake. Occasionally, Mars experiences global dust storms, where the entire planet is enveloped in a tan haze for weeks or months, the sun reduced to a faint glow. When the dust settles, it leaves a fresh coating over everything, resetting the canvas for the next whisper of wind to etch. Mars has two tiny moons, Phobos and Deimos, which are irregular, asteroid-like rocks captured by Mars's gravity. Phobos, the larger of the two, though only about 14 miles across, orbits so close that it whips around Mars in just 7.5 hours, rising in the west and setting in the east twice each Martian day. If you were near the Martian equator, you might see Phobos as a fast-moving dark blot crossing the sky, even occasionally eclipsing the sun in a brief, partial solar eclipse. Deimos, about 8 miles wide, is farther out and appears more like a bright star slowly drifting overhead. Their presence is a reminder that Mars sits at the edge of the asteroid belt and has grabbed some strays along the way. Perhaps the most tantalizing aspect of Mars is the question of life. Did life ever spark here when Mars was warmer and wetter? And if so, does anything survive today, maybe hidden underground? So far, we have not found direct evidence of past or present Martian life, but the search is actively underway. Our robotic explorers have been combing Mars for decades. The Viking landers in the 1970s conducted experiments searching for microbial metabolism in the soil. Their results were intriguing but inconclusive. In recent years, the Curiosity rover found organic molecules preserved in ancient lakebed rocks and detected methane in the Martian air that mysteriously varies with the seasons. On Earth, much methane in the air comes from microbial life or other active processes, so its presence on Mars raises eyebrows, though it could also be produced by non-biological chemistry beneath the surface. In 1996, a team of scientists announced they had found possible microfossils in a Martian meteorite, ALH 84001, that was recovered in Antarctica. Tiny structures and chemical signals that some interpreted as remnants of bacteria from Mars. The claim was highly controversial, and most researchers now attribute those features to non-biological processes. But it electrified public imagination and lent weight to the idea that Mars could have once harbored life. Today, NASA's Perseverance rover is traversing an ancient river delta in Jezero Crater, a place where a river once fed into a lake. The rover is collecting samples of mudstones and clays that, on Earth, are excellent at preserving microbial fossils. Those samples will be cached for a future mission to pick up and return to Earth in the next decade, finally allowing humanity to scrutinize Martian material in laboratories for signs of long-extinct life. Standing on Mars, one cannot escape a poignant sense of both nostalgia and hope. The ground beneath our feet is ancient and silent now, but it was once shaped by flowing water, the giver of life on Earth. The sky is foreign, tinted pinkish during the day, yet the sun that hangs there is the same sun that shines on Earth, albeit weaker and smaller. In the Martian night, if you looked up, you might even see Earth as a bright bluish star in the sky, a pinprick of life in the darkness. Mars is a world on the edge, seemingly dead today, yet holding the memory of a more vibrant past, and perhaps the potential for humans, or life in some form, to inhabit it in the future. It's no wonder Mars captivates us. It feels like a halfway house between Earth and the wider cosmos, a stepping stone into the universe. As we lift off from the dusty plains of Mars and continue outward, we pass through a sparse field of rocks and debris, the asteroid belt. Here orbit countless chunks of primordial material, from pebbles to dwarf planet-sized Ceres, all that remains of a planet that never came to be, likely kept from forming by Jupiter's strong gravity. Navigating beyond those ancient, silent stones, we emerge into the realm of the outer giants, the titans of the solar system, Jupiter and Saturn. Emerging from the asteroid belt, a new beacon dominates the darkness ahead. Jupiter, the king of planets, looms into view. Even from a distance, we can see its banded clouds and the iconic Great Red Spot, a colossal storm swirling like a crimson eye. Drawing closer, Jupiter fills our view, a tremendous striped sphere rotating rapidly. It is truly gigantic, more massive than all the other planets combined, an immense ball of gas and cloud belts. 11 Earths could be lined up across Jupiter's face. More than 1,000 Earths could fit inside its volume. As we approach, the sunlight reflected from its cloud tops bathes our spacecraft in a gentle white gold glow. Jupiter, lacking a solid surface, is essentially a deep atmosphere wrapped around a dense core. The upper layers are a tapestry of white, orange and brown cloud bands, where 400-mile-per-hour winds race east and west in alternating stripes. The Great Red Spot comes into clearer focus as we glide above Jupiter's roiling cloudscape. This storm is a vast, oval hurricane, big enough to swallow Earth whole. It has been observed for over 300 years, persisting through the centuries, though it slowly changes shape and size. Currently about 1.5 times the width of Earth, the red spot's brick-red hues stand out against the whiter bands around it. We watch it churn, a high-pressure vortex spinning counterclockwise in Jupiter's southern hemisphere, flinging clouds around its perimeter. Nearby, smaller storms, white ovals and brown barges, drift in the turbulent atmosphere. Jupiter's cloud tops are an ever-changing marbled pattern, full of eddies and flows. Lightning flashes deep within the clouds on occasion, illuminating entire cloud columns from inside for brief moments. Yet beneath the mesmerizing beauty, Jupiter is inhospitable in the extreme. If one were to descend into those clouds, the atmospheric pressure would steadily increase to crushing levels. The temperature would climb well above the boiling point of water, and sunlight would fade as dense clouds enveloped you. Deeper down, hydrogen gas, which makes up most of Jupiter, transitions under pressure first to a supercritical fluid, not quite a liquid, not quite a gas, and then, even deeper, to a state called metallic hydrogen, an exotic form of matter where hydrogen conducts electricity like a metal. There is likely a core of heavy elements at Jupiter's center, maybe the size of a few Earths, but it is buried under tens of thousands of miles of hot, dense fluid. In essence, Jupiter is more like a star that didn't quite ignite, a failed star, lacking the mass to start nuclear fusion. It emits more heat than it receives from the sun, shining with a faint internal glow at infrared wavelengths, hinting at ongoing slow contraction and residual heat of formation. Orbiting this gas giant is an entourage of moons that form a miniature solar system of their own. Jupiter has nearly 80 moons known so far, but 4 of them stand out. The Galilean moons, first seen by Galileo in 1610 with his primitive telescope. Each of these 4 is a world in its own right. Closest to Jupiter is Io, a moon about the size of our moon, but unlike any other. Io is a world of fire and brimstone, the most volcanically active body in the solar system. As our spacecraft flies by Io, we see its surface below, mottled in yellow, orange, and black. Towering volcanoes regularly erupt here, propelled by the immense tidal forces from Jupiter that flex Io's interior and keep it molten. We might catch sight of a volcanic plume, a curtain of sulfur and sulfur dioxide gas mixed with dust, arcing hundreds of miles above Io's surface, like a giant umbrella. These eruptions constantly resurface Io, painting it with fresh deposits of sulfur compounds, hence Io's striking colours. The lava lakes and calderas dotting Io make it look like a vision of hell, appropriate for a moon named after a priestess tormented by the god Jupiter. Next is Europa, slightly smaller than our moon. Europa is a smooth, bright white orb, crisscrossed with long, dark streaks, resembling cracks in an eggshell. It's one of the smoothest objects in the solar system, a clue that its surface is young and active. Europa's crust is made of water ice, and beneath that icy shell, we have strong evidence that a global ocean of liquid water exists. As we peer down at Europa, we see chaotic regions where ice rafts have broken apart and refrozen, and linear features where reddish material, possibly mineral-rich slush or organic compounds, has welled up through cracks. Europa's surface is intensely cold, around 260 degrees. But the moon's interior is warmed by tidal interactions with Jupiter and the other moons. That internal heating maintains a deep ocean that might be 60 miles, 100 kilometers deep, beneath perhaps 10 to 15 miles of ice. Where that ocean touches Europa's rocky core, hydrothermal vents could potentially exist, much like the life-bearing vents in Earth's deep oceans. Europa is thus a leading candidate in the search for life beyond Earth. We imagine for a moment plunging into that dark ocean. It would be an alien environment, sealed off from sunlight, perhaps with its own unique chemistry, and maybe even simple life forms like microbes, or who knows, something akin to jellyfish or strange fish analogues, if evolution had time and the right conditions. It's pure speculation, but tantalizing enough that future missions are being planned to probe Europa's secrets, possibly by sampling the water vapor plumes that have been detected venting from its surface cracks. Farther out orbits Ganymede, the giant among moons. Ganymede is larger than the planet Mercury and is the only moon that has its own internally generated magnetic field. Its surface is a mix of very old, dark, cratered terrain and somewhat younger, lighter regions, marked with grooves and ridges, as if Ganymede's ice-rich crust was stressed and fractured, then filled in by icy material from below. This giant moon likely has a layered internal structure with a metallic iron core, hence the magnetic field, a rock mantle, and a vast, deep ocean between the mantle and crust. That's right. Ganymede, too, might have a hidden subsurface ocean, although sandwiched between layers of ice under high pressure. Ganymede, floating silently in Jupiter's magnetosphere, experiences auroras in its thin atmosphere due to that field interacting with Jupiter's charged particles. It's a moon with a complexity that rivals a planet's. The fourth Galilean moon, Callisto, orbits even farther out. Callisto is heavily cratered everywhere, a rolling landscape of ancient impact scars that have barely changed over billions of years. If there is a record of the early solar system's bombardment, Callisto holds it on its face. Its most prominent feature is Valhalla, a huge bullseye pattern of concentric rings created by a massive impact long ago. Callisto's surface is darkish and spotted with bright ice at the rims of newer craters. Though seemingly static and dead, Callisto too might conceal a deep ocean beneath about 125 miles of ice, indicated by certain measurements of its magnetic interactions with Jupiter's field. If so, even this heavily cratered, dead moon could harbour a liquid water layer inside. Unlike its siblings, Callisto didn't undergo as much differentiation or tidal heating, and thus it's considered a more primordial body. Jupiter itself plays a crucial role in our solar system's story. Its immense gravity has been a cosmic protector of sorts for the inner planets, hoovering up or deflecting many comets and asteroids that might otherwise threaten Earth. We saw a dramatic example in 1994 when comet Shoemaker-Levy 9, which had been captured and fragmented by Jupiter's gravity, slammed into Jupiter's cloud tops in a series of spectacular collisions. Dark bruises appeared in Jupiter's atmosphere, each larger than Earth, and faded over weeks. Scars from impacts that, if they had hit Earth, would have been catastrophic. Jupiter's gravitational influence has shaped the asteroid belt, preventing a planet from forming there. And periodically, Jupiter flings celestial debris into the inner solar system or out toward interstellar space. It is a double-edged influence, at times protecting Earth, at times perhaps perturbing asteroids that eventually find their way toward us. But without Jupiter, the history of impacts on Earth might have been far more severe. We bid farewell to Jupiter's swirling beauty and its busy family of moons, and set our course for Saturn, the ringed jewel of the solar system. As we approach Saturn, it presents one of the most breathtaking sights imaginable. A golden-hued planet encircled by shining rings that span hundreds of thousands of miles. Saturn is slightly smaller than Jupiter, with about 30% of Jupiter's mass, but it's still enormous, about 9 times Earth's diameter. Like Jupiter, it's a gas giant composed mainly of hydrogen and helium, with a similarly fast rotation, about 10.7 hours per turn, that causes a noticeable flattening at its poles. The rings, however, are what make Saturn instantly recognizable. Stretching edge-on in a thin, flat plane around the planet's equator, Saturn's rings are brilliantly bright when the sun hits them. They are made of countless icy particles, ranging from grains to boulders, each orbiting Saturn like a tiny moon. When we look at them from above, we see structure, multiple rings separated by gaps. The broadest gaps, like the Cassini division, were cleared by the gravitational nudges of Saturn's moons. The main rings, named A, B, and C, are dense and bright, while fainter rings, D, E, F, and G, lie farther out or closer in. Saturn's ring system, though tens of thousands of miles wide, is incredibly thin, only about 30 feet thick on average in the main rings, almost a two-dimensional masterpiece in space. If we approach the rings closely, we'd see an almost translucent plane glinting with ice chunks. It's like flying over a vast, flat glacier made of individual pieces orbiting in unison. Occasionally, we might spot a disturbance, perhaps a tiny moonlet embedded within the rings, causing waves or propeller-like gaps as it plows through the ring particles. Saturn itself sits serenely at the center of this icy disk. Its atmosphere is more subtly banded than Jupiter's, with butterscotch and creamy white clouds. We see hints of storms. Every now and then, Saturn generates a massive storm system that wraps around the whole planet, a great white spot once per Saturnian year or so. But at the moment, the most striking weather feature is at Saturn's North Pole, the strange hexagon. Discovered by the Voyager spacecraft and later observed by Cassini, Saturn's north polar cloud pattern is a nearly perfect hexagon shape, a 6-sided jet stream circling the pole. It's an astonishing natural formation, like a geometric cloud pattern, big enough to fit 2 Earths inside. The hexagon rotates with Saturn's internal period and remains stable year after year, its origin still not entirely understood. A reminder of how even the gas giants hold surprises. Like Jupiter, Saturn is encircled by a clan of diverse moons, more than 80 known. Each adds its own chapter to the story of Saturn. The largest by far is Titan, a world larger than Mercury, and the second largest moon in the solar system, after Jupiter's Ganymede. Titan is unique. It's the only moon with a thick atmosphere, so thick, in fact, that you wouldn't see Titan's surface at all in visible light, just an opaque orange haze. Titan's atmosphere is mostly nitrogen, like Earth's, but with a smattering of methane and other hydrocarbons. It has weather and clouds and even rain, but instead of water, Titan's hydrological cycle is based on methane and ethane. As we descend, in our minds, through Titan's smoggy skies, we would witness a landscape that in some ways feels eerily reminiscent of Earth's, despite being at a frigid 290 degrees, 180 degrees. There are river channels carved into icy bedrock, flowing into dark, smooth lakes and seas of liquid hydrocarbons at the polar regions. There are vast equatorial dunes made of organic tholins, complex tar-like particles that precipitate out of Titan's air. The Huygens probe, which landed on Titan in 2005, even took pictures from the ground. Rounded pebbles of water ice lying in a dry riverbed under an orange sky. Titan is like a primordial Earth deep frozen, with a chemistry lab's worth of organic materials scattered on its surface. And beneath Titan's icy crust, yet another surprise. Gravity measurements suggest Titan too has an internal ocean of liquid water mixed with ammonia. So Titan has a dual personality. On the surface, a cold world with liquid methane, but deep down, a potential water ocean kept warm by tidal flexing and radioactive decay. Could life exist there? Perhaps not on the surface. It's hard to imagine organisms that drink liquid methane and breathe nitrogen. But maybe in the subsurface ocean, if it's in contact with rock and has energy sources. Titan pushes our definitions of habitability and is a top target for future exploration. Then there's Enceladus, a small moon only about 310 miles across that has become a superstar in the search for life. Enceladus is a bright, shiny snowball of a moon, reflecting almost all the sunlight that hits it. For a long time, it was just one of Saturn's many moons, notable for its reflective surface. But in 2005, the Cassini spacecraft made a discovery that changed everything. Enceladus is active. Cassini spotted geysers erupting from Enceladus's south pole, huge plumes of water vapor, ice particles, and organic molecules spewing out through cracks nicknamed tiger stripes. This was evidence of a subsurface ocean venting into space. Cassini actually flew through the plumes, essentially tasting them, and found salt water and a variety of organic compounds, even tiny grains of silica that hinted at hydrothermal vents on a sea bottom. In other words, Enceladus has a global liquid water ocean beneath roughly 20 miles of ice, and that ocean has energy and chemistry, the very ingredients needed for life as we know it. Enceladus instantly went from an obscure ice ball to one of the most likely places to harbour life beyond Earth. And unlike Europa's ocean, Enceladus's ocean kindly delivers free samples to space via its plumes, making it relatively easier to study. Imagining what lurks beneath Enceladus's crust. It could be simple microbes, or nothing at all. But it could also be something more complex if given time and stable conditions, is one of the most tantalizing exercises in planetary science today. Saturn's other moons each have their wonders. Iapetus, with one hemisphere as dark as charcoal and the other as bright as snow, and a mysterious equatorial ridge making it look like a walnut. There's Rhea, which might have a tenuous ring system of its own, and Dione and Tethys, each with evidence of past geological activity. Mimas, which bears an uncanny resemblance to the Death Star from Star Wars, due to a huge crater on one side. Hyperion, a chaotically tumbling, sponge-textured moon. And many, many smaller moonlets, shepherding the rings or populating Saturn's orbits. Each moon is a frozen time capsule, a piece of Saturn's extended family. As we slowly drift away from Saturn, we take one last look back. The planet appears serene and sublime. the rings now seen as a thin line glowing in the sunlight. In the darkness beyond, two tiny pinpoints, Saturn's distant moons, catch the sunlight. This corner of the solar system, dominated by giants, is rich with beauty and mystery. We have seen worlds with swirling storms, worlds with methane rains, and worlds with geysers of water. And yet, our journey is not over. Beyond Saturn, even further from the Sun, lie the ice giants Uranus and Neptune, and beyond them, the threshold to interstellar space. We press on into the dim outer reaches. Farther out beyond Saturn, the Sun's warmth has faded to a distant glimmer. In this deep cold and dimness, we encounter the seventh planet, Uranus. Uranus is a pale blue-green sphere, an ice giant planet tipped over on its side. Unlike every other planet, Uranus rotates practically on its horizontal axis. It's as though a giant hand reached out and knocked the planet over. Its axis is tilted by about 98 degrees, meaning Uranus essentially rolls around the Sun like a ball. As we approach, we see a smooth, aquamarine disk with only faint cloud features visible. When Voyager 2 flew by in 1986, Uranus appeared almost featureless, a bland cyan orb bathed in the uniform sunlight of its long seasons. In more recent observations, we've glimpsed a bit more activity. Occasional thin, white clouds made of methane ice, and even a dark spot or two marking storms in the upper atmosphere. Uranus's sideways orientation makes for bizarre seasons. Each pole gets about 42 years of continuous sunlight, followed by 42 years of darkness as the planet completes its 84-year journey around the Sun. Imagine one half of the planet languishing in constant daylight for 4 decades, while the other half lies in a frigid, starlit winter, and then they swap. During Voyager's visit, Uranus's south pole was pointed almost directly at the Sun, basking in unending sunlight, whereas much of the rest of the planet was in a dim twilight or darkness. Now, decades later, Uranus has moved along its orbit, and the formerly dark half enjoys the light. It's a world where spring and autumn are not annual events, but once-in-a-lifetime transitions. Approaching closer, we notice that Uranus is encircled by a set of thin, dark rings. They are much fainter and narrower than Saturn's broad rings, made of dark, charcoal-hued particles. These rings were discovered in 1977, when scientists noticed a star blinking out briefly several times as Uranus passed in front of it. The starlight was being blocked by ring material. Uranus's rings are composed of relatively large chunks, centimeters to meters across, of nearly black ice and rock, making them difficult to see, except when backlit by the Sun. Still, they form a graceful, if understated, adornment around the tilted planet, arranged in a dozen or so narrow bands. Small moons act as shepherds for some of these rings, corralling the particles. Uranus has a retinue of moons as well, at least 27 known. Most of them are named after characters from Shakespeare or Alexander Pope's works, a tribute to the planet's discoverer, William Herschel, and his era. The largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, range from about 500 to 1,000 miles in diameter. They are icy bodies, half rock and half water ice by composition, and each presents a unique face. Ariel, for example, has relatively few craters and many youthful surface features, suggesting some internal activity in its past. Titania and Oberon show enormous fault canyons and mysterious dark material along some craters. Umbriel is a dark, ancient surface, but with a strange bright ring on one side, nicknamed the fluorescent Cheerio, possibly a deposit from an unknown eruption. And then there's Miranda, the smallest of the 5 big moons, a true oddball. Miranda looks like it was shattered and glued back together. It has patchwork regions of wildly differing geology. One area may be ridged and grooved, another smooth with oval racetrack patterns, another dotted with colossal cliffs. In fact, Miranda boasts the tallest known cliff in the solar system, Verona Rupes, which is up to 12 miles high. If you jumped off, not that you could survive or even find footing in Miranda's weak gravity, it would take you many minutes to fall to the bottom. Miranda's jumbled appearance hints at a violent history, or perhaps extreme tidal heating that melted and refroze parts of it in the past. Uranus's atmosphere, like those of Jupiter and Saturn, is mostly hydrogen and helium, but with a higher proportion of ices, water, methane, ammonia, and others in its deep interior. The methane in the upper atmosphere is what gives Uranus its lovely blue-green tint by absorbing red light from the sun and reflecting the blues. Deep inside, Uranus likely has a slushy mantle of water, methane, and ammonia ices, hence the term ice giant, above a core of rock and metal. This mantle might form a supercritical fluid ocean where exotic chemistry occurs. Remarkably, scientists theorize that within Uranus and Neptune, pressures become so high that methane breaks down and carbon condenses into diamonds, which then rain down toward the core. Imagine entire clouds of glittering diamond crystals slowly falling through an unseen ocean inside the planet. A sparkling, if theoretical, vision of the wonders high pressure can create. Uranus challenges our imagination. It's a planet that's not only tipped over, but may literally have oceans of liquid diamond in its depths. We pull away from the pale cyan world of Uranus and venture further out. 30 times farther from the Sun than Earth, where Uranus orbits, is already a tremendous distance. Sunlight is weak and spread thin. But Neptune awaits around 30% farther still, at about 4.5 billion kilometers from the Sun. After a long journey in the near darkness, we finally arrive at Neptune, the 8th and outermost planet of the solar system. Neptune is a stunning azure blue, a true gem shining in the void. Though similar in size to Uranus, Neptune immediately strikes us as more dynamic. White clouds, likely methane ice crystals, streak its atmosphere, casting shadows on the lower layers. When Voyager 2 flew by in 1989, it spotted a great dark spot, akin to Jupiter's great red spot, raging in Neptune's southern hemisphere. By the time the Hubble Space Telescope looked some years later, that particular storm had dissipated, but new dark spots have since appeared and disappeared. Neptune's weather is intense and surprisingly active for a planet receiving only 1/900th of the sunlight Earth does. Neptune has the fastest winds measured on any planet, with jet streams that can exceed 1,200 miles per hour tearing around its latitude lines. It's a paradox. Where does the energy for such ferocious weather come from in this dim outer realm? Neptune, like Jupiter, emits more internal heat than it gets from the Sun, which likely fuels these winds. In Neptune's frigid cloud tops, around 360 DGF, 218 degrees, methane gives a rich blue color. The planet likely has a similar internal structure to Uranus, a deep mantle of water, ammonia, methane fluid, an Earth-sized core of rock and metal, and possibly that exotic diamond rain scenario playing out in its depths as well. Neptune's axial tilt, about 28 degrees, gives it seasons too, though each season lasts over 40 Earth years due to Neptune's long 165-year orbit. In 2011, Neptune completed its first full orbit since humans discovered it in 1846, as if to remind us how far out it really is. Neptune carries a system of rings as well, but they are faint and dusty, visible mainly through careful imaging or when backlit by the sun. These rings are clumpy. The outermost Adam's ring has peculiar bright arcs where ring particles bunch up. It's believed that gravitational interactions with one of Neptune's moons, Galatea, keep those arcs confined. The existence of arcs defies the expectation that rings should spread out evenly. It took Voyager's flyby to reveal this odd configuration, which scientists are still modelling to fully understand. Neptune's moons number over a dozen, but one dominates: Triton. Triton is a moon almost as large as our moon, and it's unique because it orbits Neptune in the opposite direction to Neptune's rotation, a retrograde orbit. This suggests Triton was likely a Kuiper belt object, much like Pluto, that Neptune captured long ago. The capture may have been a violent, disruptive event that led to other original moons being lost or smashed, and Triton settling into a backward orbit. Triton is one of the coldest places measured in the solar system, with a surface temperature around 391 degrees 235 degrees. Yet, when Voyager 2 flew past, it saw something astonishing: geysers. Dark plumes, likely of nitrogen gas carrying dark dust, were erupting from Triton's icy surface and lofting material up to 5 miles high. These plumes then drifted downwind, leaving streaky deposits on the pinkish ice. Triton, like Enceladus, has active geysers, although powered by a different mechanism, probably solar heating of a thin dark layer causing subsurface nitrogen ice to vaporize and jet out. Triton's surface, as imaged by Voyager, showed young plains with what looked like melted terrain, as well as strange cantaloupe textures in some regions. It is thought that Triton, despite its deep freeze, might also have a subsurface ocean, or at least pockets of liquid deep inside, warmed by tidal flexing when it was first captured, and perhaps still continuing to some extent. Triton has a tenuous atmosphere as well, a thin layer of nitrogen that snows out onto the surface when Triton's long winter sets in. The rest of Neptune's moons are much smaller and irregularly shaped, likely captured asteroids or fragments from collisions. One of them, Nereid, has an extremely elongated orbit, suggesting it was disturbed when Triton was captured. Proteus, Neptune's second largest moon, is a dark, cratered world that's as big as an object can get without its gravity pulling it into a sphere. Proteus is still irregular in shape. These moons quietly accompany Neptune on its solar journey, circling in the far twilight of the sun. Now, as we take leave of Neptune, we have essentially traversed the planetary portion of our solar system. Standing at Neptune's distance, the sun is a small but intensely bright point of light, no longer the warming orb we know at Earth. The idea of warmth and daylight feels distant. The 8 major planets we've explored each offered something unique, from Mercury's boiling and freezing rock to Neptune's windy azure skies, but all of them still bask in at least a little of the sun's light. Beyond Neptune, we enter a new realm, the kingdom of ice and shadow, where the sun's influence wanes, but is not gone entirely. The solar system does not end at Neptune. It stretches outward through a vast cloud of small frozen worlds and fragments. We now venture into this distant region, exploring the dwarf planets, comets, and icy debris that reside in the dark frontiers. Crossing Neptune's orbit, we slip into the outermost province of our solar system. Here the sun is but a tiny, distant light, and space is bitterly cold. Yet this darkness is not empty. We enter the Kuiper belt, a vast ring of icy bodies encircling the sun beyond the major planets. Among these frozen relics drifts Pluto, once considered the 9th planet of our solar system. Pluto appears as a small, mottled sphere of white, red, and brown, illuminated faintly by the distant sun. In 2015, the New Horizons spacecraft flew past Pluto and unveiled an astonishingly complex world. we glimpse a bright, heart-shaped region on Pluto's surface, informally called Tombor Regio. One lobe of this heart, Sputnik Planitia, is a vast plain of nitrogen ice. Its surface is divided into polygonal cells, hinting at slow convection churning the ice over time. This area is strangely free of impact craters, indicating it is geologically young. Perhaps the surface has been renewed by the slow, overturning circulation of nitrogen ice, or even an underground ocean pushing up from below. At Pluto's edges rise rugged mountains, some as tall as 11,000 feet. But these are not rock, as on Earth. They are mountains of water ice, as hard as stone in Pluto's frigid climate. Elsewhere, we see regions coated with a dark reddish hue, likely complex organic molecules, tholins, created by sunlight acting on methane in Pluto's surface and atmosphere. Pluto has a tenuous blue-tinged atmosphere of nitrogen that expands when the planet is near the Sun, and then partially collapses as it moves farther out on its elliptical 248-year orbit. As we soar above Pluto's terminator, the line between day and night, we are treated to a hazy twilight. The sun's rays, filtering through the atmosphere, create layers of blue haze, silhouetted against the black of space. It's a surprisingly beautiful sight for such a distant world. The temperature at Pluto's surface is around 375 degrees, 225 degrees. In this deep cold, ices of nitrogen, methane, and carbon monoxide behave almost like water does on Earth. They can flow or sublimate. Pluto's surface and climate seem bizarre, but also somewhat Earth-like in the sense of having active cycles, albeit with very different materials. Accompanying Pluto on its journey is its large moon, Charon. Charon is so big, about half Pluto's diameter, that Pluto and Charon together orbit a point in space between them, like a dumbbell. Charon's gravity is significant enough that we should really think of Pluto-Charon as a double dwarf planet system. Charon's surface is different from Pluto's. It's more uniformly grey, covered largely in water ice. It has craters and some young fractures, and a prominent dark reddish cap at its north pole, nicknamed Mordor Macula, likely formed from gases escaping Pluto and chemically changing on Charon's surface. A giant chasm runs across Charon, a canyon far longer and deeper than Earth's Grand Canyon, possibly created as Charon's interior cooled and expanded. At some point in Charon's past, there might have been a subsurface ocean that froze, cracking the surface. Pluto and Charon are tidally locked, always showing the same face to one another in their slow dance. If you stood on Pluto, Charon would hover in the same spot in the sky, if you were on the hemisphere that faces Charon, and vice versa. They are like two partners, perpetually gazing at each other across space. Pluto is not alone in the Kuiper Belt. As our craft travels beyond Pluto, we encounter other distant dwarfs lurking in the darkness. There is Eris, a world almost the same size as Pluto, just slightly smaller in diameter, but more massive. Discovered in 2005, Eris orbits the Sun on a highly elongated path that takes it much further out than Pluto at times. It can be almost 100 Earth-Sun distances, 100 AU, away at aphelion. Eris has a tiny moon named Dysnomia. The discovery of Eris is what provoked the debate that resulted in Pluto's reclassification as a dwarf planet. Suddenly, Pluto was not unique, but merely one of a new class of numerous Pluto-like objects. We have Makemake, another dwarf planet out here, with a slightly reddish tinge and a very small moon. And Haumea, an elongated, rapidly spinning dwarf planet, shaped a bit like an egg or football, with two known moons and a faint ring system of its own. Haumea's rapid spin, a day of about 4 hours, flung it into that distorted shape, and possibly shed icy fragments, maybe its moons or ring material. These names, drawn from mythologies of creation and the distant past, barely scratch the surface of the population of Pluto-like objects in the Kuiper belt. Astronomers suspect there are hundreds, perhaps thousands, of bodies, hundreds of kilometers across out here, and countless smaller ones. They are remnants from the solar system's formation, planetesimals that never coalesced into a larger planet, preserved in the deep freeze. Some objects, like one called Sedna, follow highly elongated paths that carry them thousands of AUs away at their farthest point. Their orbits are mysteriously aligned with one another, hinting that an unseen influence, perhaps even a yet undiscovered massive planet lurking in the far darkness, might be shepherding these distant bodies. This hypothetical Planet 9, if it exists, could be several times Earth's mass and orbit, hundreds of times farther out than Neptune, waiting to be discovered by future sky surveys. As we venture further outward, the Kuiper belt begins to thin out. This is the Oort cloud, a hypothetical shell of cometary material tens of thousands of times farther from the Sun than Earth. No spacecraft has ventured there, and no one has observed Oort cloud objects directly. They are too small and too far. But their presence is inferred from the fact that long-period comets, those that arrive on orbits thousands of years long from all directions, must originate from a distant reservoir. The Oort cloud would be the deep freeze archive of the solar system's birth, consisting of trillions of icy nuclei silently orbiting the Sun at the edge of interstellar space. Occasionally, a passing star, or the tidal forces from the Milky Way's collective gravity, disturb this cloud, sending one of its small members plummeting toward the inner solar system. When that happens, what was once an invisible ice ball in the outer darkness becomes one of the most spectacular sights in the night sky, a comet growing a glowing tail. Imagine now that we are no longer on a spacecraft, but witnessing the journey of one such comet. At first, it's just a dark, solid lump a few miles across, drifting quietly in the far, cold reaches. As it falls inward, drawn by the Sun's distant gravity, the feeble sunlight grows stronger. By the time it reaches the outer planet's region, the Sun's warmth begins to have an effect. The comet's surface, a mix of ices, water, CO2, ammonia, methane, and dust, warms enough that ices start to sublimate, turn directly from solid to gas. Jets of vapor hiss out from patches on the sunward side, carrying dust with them. A fuzzy aura of gas and dust, called a coma, forms around the nucleus, shrouding it in a hazy glow that grows in size and brightness as the comet approaches the Sun. When our comet passes the orbit of Jupiter and comes nearer to the inner solar system, it transforms dramatically. Solar radiation and the solar wind push on the expanding coma, stretching it into two immense tails. One tail is made of electrically charged gas molecules, ions, and is blown straight back by the solar wind. It often glows blue due to ions like carbon monoxide fluorescing in sunlight. The other tail is made of dust particles, which are heavier and lag behind, forming a broader, curving tail that often looks white or yellow as it scatters sunlight. These tails can extend millions of miles across space, a glorious banner heralding the comet's approach. If such a comet becomes visible from Earth, people might see it as an awe-inspiring spectacle in the dawn or dusk sky, a bright head with filaments trailing far across the stars. Throughout history, comets have been viewed with wonder, reverence, and not a little fear. Now we understand that they are neither omens nor miracles, but time capsules, leftover building blocks from the solar system's formation, come to visit the inner sunlit realm for a brief time. Our comet circles the Sun at perihelion. perhaps a few tens of millions of miles from the Sun at its closest. It then heads back out, its once full reservoir of surface ice depleted a bit by the recent display. Eventually, it will either disintegrate, as some comets do after many passages, or retreat to the depths for decades, centuries, or millennia until it returns again, or possibly never, if its orbit is altered enough to escape the Sun entirely. Meanwhile, as it swept through the inner solar system, that comet may have left a subtle legacy, dust from its tail strewn along its orbit. If Earth's path intersects that stream of particles, we on Earth will enjoy a meteor shower as tiny grains burn up in our atmosphere, a gentle reminder of the comet's journey. Comets likely played a crucial role in Earth's early history by delivering water and organic compounds. In the chaotic early solar system, a rain of comets and asteroids, the late heavy bombardment, pummeled the inner planets. Earth's oceans may have been partly filled by cometary water. Complex molecules that are precursors to life, such as amino acids, have been detected in comet material. For instance, the Rosetta probe's lander, Philae, found such molecules on comet 67P Churyumov-Gerasimenko. Thus, the same objects once seen by our ancestors as heralds of doom could well have been bearers of the seeds of life. Comets and asteroids have also caused periodic catastrophes on Earth. Most famously, a roughly 6-mile-wide object, likely an asteroid, but could have been a comet, struck Earth 66 million years ago, leading to the mass extinction that ended the reign of the dinosaurs. In that sense, these small bodies are entwined with life's fragility and resilience. Having followed a comet's path back out toward the fringes of the solar system, we now truly stand at the threshold of interstellar space. The Sun's influence extends a bit further still. The solar wind continues until it encounters the galactic medium in the heliopause, out around 100 to 120 AU, where Voyager 1 and 2 have now passed into that realm of interstellar space. But in terms of objects bound to the Sun, the Oort cloud may reach out to 50,000 AU or more, nearly a light year. Beyond that, the pull of other stars and the galaxy begins to dominate. Our exploration of the solar system, from the Sun's fiery core, through the rocky inner worlds, the gas and ice giants, and the cometary halo, reveals a cosmos full of marvels. Each step of the way, we've encountered something astonishing. Planets with unimaginable conditions, moons that hide oceans beneath ice, and primordial remnants carrying the ingredients of life. But as far as we've come, we have only been voyaging within one star's family. Beyond the solar system, scattered across the vastness of space, are countless other stars. And we now know that many, if not most, of those stars host their own planets. The night sky we gaze up at is not just a tapestry of lights. It's a map of other suns, each with possibilities. It's time to leave our sun's neighborhood and journey to those new worlds, exoplanets orbiting distant stars, to see what wonders they hold, and to ask the question, could we have company in this universe? Beyond the confines of our solar system, the night sky is filled with stars as far as the eye can see. For generations, humans have wondered if those distant suns have their own planets, other worlds like the ones we call home. It was long an open question, fodder for science fiction and speculation. But now, in our time, the answer is known. The universe of planets has opened up. We have discovered thousands of exoplanets, over 5,000 confirmed so far, orbiting other stars, and we suspect there are billions more waiting to be found. As our journey continues outward, imagine drifting away from the sun and toward one of those stars twinkling in the darkness. Each star is a sun in its own right, and around many of them, planets are circling. The once empty gulf between stars, we now realize, is populated by these other solar systems. The first exoplanets discovered were strange by our standards. Giant planets hugging so close to their stars that their years last mere days and their heated atmospheres puff up with starlight. In fact, the very first confirmed discovery of planets beyond our solar system came in 1992, around an even more bizarre host, a pulsar, the rapidly spinning neutron star left behind by a supernova explosion. Detecting planets circling this tiny dead star was a shock, but it proved that planets can exist in astonishingly extreme environments. Then in 1995, astronomers found a planet around 51 Pegasi, a star not unlike our Sun. This planet, 51 Pegasi b, turned out to be a hot Jupiter, a gas giant roughly half the mass of Jupiter, but roasting close to its star, whipping around in just about 4 Earth days. It was completely unlike the neatly ordered solar system we knew and challenged our theories of planet formation. Yet there it was, and soon many more followed. We found Jupiter-like planets skimming their stars' surfaces, Neptune-mass worlds parked scorchingly near their suns, and so on. These discoveries showed that planetary systems can arrange themselves in wild and unexpected ways. We detect these far-off worlds, mostly indirectly, by watching the stars for subtle clues. Often, a planet will transit in front of its star from our point of view, causing the star's light to dim slightly at regular intervals. This transit method has been extraordinarily successful. Space telescopes like Kepler stared at fields of stars and caught these tiny dips in brightness, indicating a planet's silhouette crossing the star. Each dip is tiny, like a fraction of a percent in starlight, but telltale if it repeats periodically. Using this method, we've identified thousands of exoplanets, from scorching hot worlds to temperate ones. Another technique is radial velocity. A star wobbles very slightly due to the gravitational tug of orbiting planets. By looking for shifts in the star's spectrum, its light's color signature, caused by it moving towards or away from us, we can infer the presence of a planet and even estimate its mass. Even in a few cases, astronomers have directly photographed exoplanets by using advanced optics to blot out the blinding starlight, revealing the planets as faint points of light orbiting their stars. With these methods and more, the once empty catalogue of known planets beyond our solar system has grown into a rich menagerie. As we tour this menagerie in our imagination, the diversity of worlds is astonishing and far greater than what we have in our own solar system. There are scorched, ultra-hot Jupiters so close to their stars that their day sides are thousands of degrees and their atmospheres puff out and even get stripped away. On one such planet, it's daytime forever on the star-facing side and nighttime forever on the far side due to tidal locking. The day side might even harbour clouds of silicate particles, essentially clouds of tiny glass, that rain molten droplets. There are gas giants in eccentric, comet-like orbits, swinging from close to far from their star. There are super-Earths, planets a bit larger than Earth, up to about 10 times Earth's mass, which could be rocky or water-rich or something in between. We've found mini-Neptunes, smaller versions of our ice giants, that blur the line between rocky planet and gas planet. Some exoplanets orbit 2 stars at once, like the fictional Tatooine of Star Wars. Imagine standing on such a world and seeing a double sunset as 2 suns dip below the horizon. One particularly fascinating discovery has been the TRAPPIST-1 system. TRAPPIST-1 is a tiny, dim red dwarf star about 40 light-years away, and around it orbits a compact family of 7 Earth-sized planets. The innermost ones are quite hot, but 3 of them lie in the star's habitable zone, where temperatures could, in principle, allow liquid water on the surface if conditions are right. These planets are all packed in closer to their star than Mercury is to the Sun. If you were on one, the neighbouring planets might loom large in the sky, in some cases larger than our Moon looks to us. Because TRAPPIST-1 is a cool red dwarf, the habitable zone is very close in. Likely all 7 planets are tidally locked to the star, meaning the same side of each planet always faces the star. If so, each world has a perpetual day side and a perpetual night side. Picture standing in the twilight band on one of these worlds, say TRAPPIST-1e, one of the potentially habitable ones. Ahead of you, the red dwarf sun hangs low, not moving, casting a coppery light. Behind you stretches an endless night. Overhead, perhaps, you might spot another planet, a crescent in the sky. It's a scenario utterly unlike Earth, yet the size of these planets and their potential for water makes them compelling targets in the search for life. Another remarkable system is around the star Kepler-16, where the planet Kepler-16b orbits a binary pair of stars. Here, you would truly have a double sun in the sky, a K-type orange star and an M-type red dwarf dancing around each other, with the planet looping around them both. Sunsets, 2 of them, might be spectacular. While Kepler-16b is a cold gas giant, uninhabitable to life as we know it, its existence proves that circumbinary planets, planets around double stars, are possible. Indeed, nature seems to find ways to put planets in all kinds of configurations, even ones we thought might be too unstable. Among the thousands of exoplanets discovered to date, a few have generated special excitement because they are small and temperate, the kinds of worlds that could potentially host liquid water and, by extension, life. We've found several Earth-sized planets in the habitable zones of red dwarf stars. Proxima Centauri b is one famous example, orbiting our nearest stellar neighbour, Proxima Centauri, just 4.2 light-years away. The good news, it's roughly Earth-sized and in the habitable zone of its faint red star. The less good news, Proxima is a very active red dwarf that throws off flares which could strip an atmosphere, and Proxima b orbits so close, a 11-day year, that it's probably tidally locked. Still, if it has a strong magnetic field or an ocean, who knows? It could possibly retain an atmosphere and maybe some form of life. Then there's a planet like LHS 1140b, a super-Earth about 7 Earth masses, also in the habitable zone of a red dwarf, which is considered one of the more promising habitable zone worlds for atmospheric studies, because the star is relatively quiet and the planet is dense and likely rocky. We have also begun to find planets around stars, more like our Sun, that might be somewhat Earth-like. Kepler 452b, sometimes dubbed Earth's cousin, is one example. It orbits a Sun-like star at a distance similar to Earth's, though the planet is bigger, about 1.6 times Earth's radius. If it's rocky, it might have gravity about twice Earth's, and an atmosphere thicker than ours. It could be something like a super-Earth version of our planet, though it might also be more Neptune-like, with a big gas envelope. Another, Kepler-62f, orbits a somewhat cooler star, but is squarely in that star's habitable zone, and is just about 40% larger than Earth. A tantalizing candidate for a water-ocean world, perhaps. The truth is, many of these potentially earthy planets orbit stars that are quite different from our Sun, often smaller and redder, and we don't yet have the capability to know much about their atmospheres or surfaces. We often don't know if they have thick clouds of CO2, like Venus, or perhaps no atmosphere at all. But the mere presence of so many candidates is encouraging. Statistically, it appears that in our galaxy, there could be on the order of billions of rocky planets in habitable zones around their stars. Whether any of those are truly habitable or inhabited remains the grand question. To answer that question, scientists are eager to study exoplanet atmospheres for biosignatures, signs of life's activity. Already, using current technology, we have been able to analyze the atmospheres of some exoplanets, primarily big, hot ones. The Hubble Space Telescope, and now the James Webb Space Telescope, JWST, have detected things like water vapor, methane, and even clouds and haze in the atmospheres of certain gas giants or sub-Neptunes. JWST, in its first year of exoplanet observations, revealed clear signs of carbon dioxide in the atmosphere of WASP-39b, a hot Saturn mass planet, the distinct signature of photochemical haze on another, and even hints of more complex chemistry on a few. It has the sensitivity to perhaps, just maybe, detect things like oxygen or other biomarkers in the atmospheres of a few favorable small planets. But that remains extremely challenging. The first realistic chance to detect an Earth-like atmosphere with oxygen, water vapor, etc. on an exoplanet might come from future observatories designed specifically for that task, perhaps a decade or two from now. Nonetheless, we are on the threshold of being able to probe the air of worlds tens of light years away. Imagine the thrill if one day soon we aim our telescopes at a small, rocky exoplanet in its star's habitable zone and find a combination of gases that screams life. For instance, large amounts of oxygen alongside methane, or perhaps chlorophyll-like pigments, which might be detectable as a subtle change in how the planet reflects light at certain colors, a red edge, as vegetation on Earth shows. It would be a discovery for the ages, evidence that biology is not unique to Earth. Even short of that, just knowing what these distant worlds are like is enthralling. Some exoplanets may turn out to have global oceans and steamy atmospheres. Others might be dry, cratered rocks. Some could be completely shrouded in clouds like Venus. The diversity, even within the relatively small sample we've studied, hints at myriad possibilities. The search for life also encompasses listening for artificial signals, SETI, and looking for technosignatures, like unusual optical or infrared emissions that might indicate technological activity. So far, we haven't found anything conclusive on that front. But the exoplanet revolution has given SETI a more focused target list. We know exactly where the potentially habitable planets are, around which stars. If any of those are broadcasting or leaking radio waves, we have a better idea of where to point our antennas. The silence so far could mean intelligent life is rare, or just that it's quiet or too distant. But with each new Earth-sized planet found, one can't help but wonder, if some of them have life-bearing environments, what forms might that life take? Even simple alien microbes would be profound to discover. The question of whether we are alone in the universe feels a bit less abstract now that we can actually envision thousands of other worlds and identify some that might be kindred to Earth. Our journey through exoplanets lets us imagine some truly wondrous scenes. Picture an Earth-like planet in the habitable zone of a sun-like star. Perhaps it has continents and oceans, maybe a moon like ours. Its inhabitants, if any, would see a familiar yellow sun and perhaps wonder about planets around other stars, like ours. Or picture a planet around a red dwarf, its sky bathed in dim red light. Maybe plants, if they existed, evolved to be black or dark to absorb as much of the scant energy as possible. Or a super-Earth with a dense atmosphere and high gravity, where creatures, if they existed, might be squat and strong to handle the weight, and perpetual cloud cover might hide the stars entirely from view. Nature's imagination seems endless, and through exoplanets we get to sample that cosmic creativity. Even as we revel in the discovery of exoplanets, these findings also cast our own world in a new light. We realize that a planet like Earth, with its particular size, composition, water content, large moon, stable star, might be rarer than we thought, or maybe common. We still aren't sure. But we do know that Earth has something no other known planet has, that we've confirmed. An active biosphere with intelligent life capable of building radio telescopes and probes. We have yet to find a true twin of Earth with a breathable atmosphere and abundant life out there. It might be out there waiting, or it might be vanishingly uncommon. Either way, seeing so many other planets underscores both the potential for finding another Earth and the preciousness of the one we have. Our exploration in this part of the documentary has taken us on a grand sweep. From our sun's fiery birth and its family of planets, all the way out to the icy edge of the solar system, and then beyond, to alien worlds orbiting alien suns. We travelled in our minds across unimaginable distances, yet we have only scratched the surface of the cosmos. Planets are just one piece of the cosmic puzzle. Beyond the planets, the universe holds even larger and more energetic phenomena. In the next part of our journey, we will turn to the stars themselves, those glittering furnaces scattered throughout the galaxy, and to the structures that bind them, the galaxies, and the cosmic web beyond. We will witness how stars are born, live, and die in spectacular explosions, how black holes twist the fabric of space, and how the universe as a whole began, and where it might be heading. Our cosmic journey is far from over. It is about to enter a new chapter, taking us into the deeper mysteries of the universe itself. As our cosmic journey continues, we drift further into the silent wonders of the universe. We have marveled at galaxies and stars, at black holes and supernovae, and felt the gentle hum of cosmic history around us. Now the voyage carries us onward, into new realms of discovery. In the stillness of space, we turn our attention to the frontiers that lie ahead, the challenges and hopes as humanity stretches its presence beyond the cradle of Earth. The darkness of space is vast and quiet, a perfect canvas for the next chapter of exploration, painted in calm tones and endless curiosity. Out in the weightless void, even our own bodies begin to change. Free from gravity's pull, astronauts float effortlessly, but their physiology quietly shifts. Blood and fluids drift upward toward the head, no longer drawn down to the feet. Faces become puffy, and noses feel constantly congested. In microgravity, the body's sense of up and down fades away, and every direction feels the same. It is a strange, dreamlike state, as if the body must learn a new way of being, gently adapting to the freedom of weightlessness. Without gravity's resistance, muscles no longer need to work as hard. Day by day, they grow weaker and shrink, especially the muscles that once held us upright against Earth's pull. Astronauts must exercise for hours each day, quietly pedaling stationary bikes or pulling against resistance bands in their spacecraft. In the calm of the space station, you might hear the soft whir of a treadmill as an astronaut jogs in place, tethered by bungee cords. This daily ritual fights the gradual fading of strength, keeping the body toned and ready for the day it must return to Earth. Bones, too, respond to the lack of gravity. On Earth, our bones bear our weight, constantly regenerating to keep us strong. In space, freed from weight, bones begin to thin. Calcium gently leaches out into the bloodstream. Over weeks and months, an astronaut can lose significant bone density, almost as if aging rapidly. It's said that without countermeasures, astronauts might lose 1 to 2% of bone mass per month in space. But like a caring guardian, science intervenes. Vitamin D supplements, resistance exercises, and careful diets help slow this bone loss. Still, when explorers finally come home, their bones will need time to rebuild under the familiar pull of gravity. Even the heart adapts to microgravity's quiet conditions. The heart no longer works as hard to pump blood upward, so it can relax a little. Over time, it may become slightly smaller or more spherical. Heart rate and blood pressure shift. In the tranquil floating environment, an astronaut's heart doesn't need to beat as forcefully as it did on Earth. Yet this gentle reduction in workload means that when back on solid ground, the heart must quickly readjust to normal. That is why returning astronauts often feel lightheaded or weak until their cardiovascular system regains its Earth strength. The senses also encounter surprises. Without the usual cues of up or down, the inner ear, our balance organ, gets confused. In the first days of weightlessness, many astronauts feel a wave of motion sickness. Their brains struggle to interpret a world where the floor no longer exists. But gradually, the body finds a new equilibrium. The nausea fades, and a peaceful ease sets in as floating becomes second nature. Astronauts often remark how after adapting, moving through the station feels like swimming through air with graceful, slow motions. However, microgravity isn't the only challenge. Space is not a gentle environment, and radiation is an invisible companion on every journey. Beyond Earth's protective magnetic field and atmosphere, cosmic rays and solar radiation stream through spacecraft walls, quietly altering cells. Over a long mission, the accumulated radiation exposure is much higher than on Earth. It can increase cancer risk or cause subtle changes in the body. Astronauts take precautions, shielding themselves as much as possible. During intense solar storms, they retreat to protected areas of their ship, letting walls and water tanks absorb the worst of the charged particles. In the hush of space, they wait out the storm, knowing that safety sometimes means simply finding a quiet corner away from the invisible rays. Eyes and vision can also be affected by living in microgravity. Over time, some astronauts experience a curious change. Their eyesight shifts, often becoming a bit more farsighted. In the serene darkness of space, with fluids shifting into their head, pressure can build behind the eyes. This condition, sometimes called spaceflight vision syndrome, leads to the eyeball slightly changing shape. Astronauts might notice that reading checklists up close becomes a little blurrier than before. Scientists are still studying this effect, trying to understand and mitigate it. For now, astronauts carry an extra pair of glasses or special adjustable lenses, just in case their vision changes during the mission. Even sleep in space has its quirks. Astronauts experience 16 sunrises and sunsets each day as their station circles Earth every 90 minutes. To keep a regular schedule, they follow Earth time and zip themselves into sleeping bags attached to the wall or ceiling. In microgravity, there's no need for a bed. One can drift off in any orientation, cradled by the sleeping bag to prevent floating around. Some say that sleeping in space can be very restful, like being a baby held in 0G. Still, it can take time to truly relax. Without the familiar pull of gravity, the body isn't sure how to let go completely. Sometimes astronauts report strange dreams, or waking up unsure which way is up. Soft eye masks and earplugs help create an artificial night amid the constant hum of the station's life support systems, easing them into sleep even while the universe outside cycles from day to night every hour and a half. The psychological side of space travel is another frontier. The silence of space outside contrasts with the confined quarters inside a spacecraft. Astronauts live for months in a metal habitat about the size of a small apartment, with the same few crewmates. Far from home, they float by the window and gaze at Earth, a glowing blue marble against the blackness. This sight brings comfort and perspective. Many astronauts describe the profound feeling of seeing their entire home world hanging in the void. It reminds them of how interconnected and fragile life on that planet is. In quiet moments, they think of loved ones far below, or reflect on the journey that brought them to this point. Isolation and confinement can be stressful, even in the calm routine of orbital life. Each crew member finds their own ways to cope. Some listen to music on little headphones, drifting gently as melodies remind them of home. Others keep busy with experiments and tasks, structuring their day with purpose. Communication with family, via radio or video, though delayed, becomes a treasured event. There is solace in the camaraderie of the crew, a small family united by a mission. In moments of leisure, astronauts gather at the window to share a meal and watch continents slowly pass beneath, not needing words to share their wonder. On the night side of Earth, they trace networks of city lights shimmering in the darkness, watch silent thunderstorms flash with gentle pulses, and see the hazy band of the Milky Way arching overhead. These simple sights bring a comforting sense of connection to home, even amid the vastness. To keep minds sharp and spirits up, astronauts schedule fun activities too. They might have movie nights with a laptop secured to a wall, or play with weightless toys, laughing as a water droplet floats between them. On special occasions, they even enjoy treats, perhaps rehydrated ice cream or a favorite meal sent up from Earth. These small comforts bring warmth to the cold of space. They remind everyone that though they are far from Earth, they carry the essence of home with them. Through all these adjustments, the human body shows an impressive ability to adapt. From the muscles and bones to the heart and mind, we learn to live beyond our home planet's gravity. Each astronaut's journey is also an experiment in how life can endure in places utterly different from where it began. The data gathered, from bone scans to personal journals, helps doctors and scientists plan for even longer voyages. If humans are to travel to Mars or drift for years through deep space, we must solve these challenges of the body and spirit. Already, ideas are emerging to aid future explorers. Scientists imagine spacecraft that spin slowly to create a gentle artificial gravity, so travelers might stroll under a simulated weight, their bones and muscles no longer fading. Engineers design improved shielding to block cosmic radiation, perhaps using water or new materials to wrap spacecraft in a protective embrace. Research into hibernation-like sleep is underway, pondering if astronauts might one day doze through long journeys, their bodies preserved in rest to minimize psychological strain and conserve resources. Space medicine expands with each mission, quietly ensuring that when humanity takes its next big leap, we are ready. Every lesson learned on the International Space Station or during missions to the Moon becomes a stepping stone. Our bodies are resilient, but require care in the alien environment of space. In this gentle contest between human biology and the cosmos, we are finding a balance, a way to coexist with weightlessness and radiation, to thrive in what was once unlivable. Imagine an astronaut on a voyage to Mars. She drifts near a window, watching the distant sun, while sensors monitor her heart and muscles. She follows a routine of exercise and rest, work and reflection. Day by day, her body stays strong, and her mind remains focused, thanks to decades of knowledge gained by those who went before. In the solitude of interplanetary space, she knows that her journey is possible because humans have learned to live out here, in this silent expanse. In the tapestry of exploration, caring for the explorers is as vital as reaching the destination. The quiet triumph of space medicine is that it allows us to venture further, turning what were once great physical obstacles into manageable parts of life off-world. Gently, steadily, we extend our home into space, not just with metal ships, but with our very flesh and blood, adapting to the cosmos. It's a humbling and inspiring thought. Even as we float free from Earth, we carry a piece of Earth within us. Our bodies learn to dance to a new cosmic rhythm under ageless stars. As we learn to live beyond Earth, we also realize how precious and fragile our home is. The cosmos is filled with wonders, but it also holds occasional dangers. From time to time, rocky visitors from space cross Earth's path. Long ago, one such visitor, a mountain-sized asteroid, ended the age of the dinosaurs. 66 million years in the past, under a peaceful Cretaceous sky, that massive rock struck our planet with unimaginable force. The impact carved a vast crater and shrouded the world in dust and darkness. Most life perished in the global winter that followed, and the course of evolution changed. It was a catastrophic yet pivotal moment that eventually made room for mammals, and ultimately us, to thrive. Now, for the first time in Earth's history, a species has the knowledge and tools to see an asteroid coming and do something about it. Today, humanity stands as a watchful guardian. We scan the skies with telescopes, mapping the orbits of asteroids that come near our planet. We also take comfort in natural guardians like Jupiter. The giant planet's gravity often pulls in comets and stray rocks that might otherwise wander toward the inner solar system. In 1994, astronomers watched as a comet named Shoemaker-Levy 9 broke into pieces and slammed into Jupiter's atmosphere, leaving dark scars on the gas giant. It was a dramatic reminder that bigger worlds can shield smaller ones. Our solar system can be a dangerous place, but we have allies in the dance of the planets. Each day, astronomers quietly track faint moving points of light against the starry background, identifying new space rocks and calculating their paths decades into the future. Thousands of near-Earth asteroids have been catalogued. Most are small and harmless, burning up as beautiful shooting stars if they ever enter our atmosphere. But some are larger, big enough to cause damage if they were to strike. Thankfully, we have found nearly all the truly enormous asteroids that could threaten civilization, and none currently pose an imminent risk. Yet we remain vigilant, watching for the smaller, but still dangerous ones that could strike with the force of a nuclear blast. Our watchfulness has already paid off with early warnings. In 2029, a known asteroid named Apophis will pass remarkably close to Earth, coming nearer than some satellites. For a while after its discovery, scientists worried about a possible impact in the distant future. But with careful observation, they ruled out any collision for at least a century. When Apophis flies by, people in some parts of the world will see a bright point streaking across the sky, a reminder of how far our ability to predict cosmic events has come. Instead of fear, we will watch with knowledge and confidence in our calculations. Still, the cosmos likes to surprise us. In 2013, under a calm morning sky in Russia, an unexpected visitor arrived. A small asteroid, roughly 20 meters across, pierced the atmosphere above the city of Chelyabinsk. It exploded high in the air with a flash brighter than the sun, sending out a powerful shockwave. Windows shattered across the city as the boom echoed, and over 1,000 people were injured by flying glass. Thankfully, the object disintegrated before reaching the ground, and no one was killed. This wake-up call from nature showed that even modest-sized meteors can have dramatic effects. It pushed us to improve our sky surveys, to catch these stealthy space rocks before they catch us off guard. To truly defend our planet, detection alone is not enough. We also need methods to prevent a collision if one ever looms. In a remarkable test of our planetary defense capabilities, scientists launched the DART mission, a small spacecraft with a big purpose. In September 2022, after a quiet journey through space, DART deliberately slammed into a tiny asteroid moonlet called Dimorphos. The target posed no danger to Earth. It was chosen as a safe trial. The collision was like a gentle cosmic nudge, but it successfully altered Dimorphos's orbit around its parent asteroid. For the first time, humanity proved we can change the path of a celestial body. It was as if we learned to deflect a coming pebble with a precise flick of a finger. The success of this mission was measured in minutes. After impact, Dimorphos began circling its companion a little faster, its orbital period shortened by roughly half an hour. That subtle shift was exactly what engineers hoped for. If we ever find an asteroid on a collision course, a similar approach could be used years in advance. A spacecraft impact, or another technique to slightly tweak its trajectory, so that by the time it would have reached Earth, it drifts harmlessly off course. It's reassuring to think that with careful preparation, a once inevitable disaster could be averted by a well-timed push. Other creative strategies are being explored too, many of them elegant and slow-acting. One idea is a gravity tractor, stationing a spacecraft near an asteroid and letting the tiny gravitational pull between them tug the asteroid gradually onto a different path. Over months or years, this quiet tug could add up to a big change in where the rock will travel. Another concept imagines using the power of sunlight. By painting or dusting one side of an asteroid a different color, we could change how it absorbs and radiates heat, causing a slight but steady push on its orbit. These approaches emphasize gentle persuasion over brute force, aligning well with the patient rhythms of space. In dire scenarios where time is short, more dramatic measures have been contemplated, such as using nuclear explosives to either shatter a smaller asteroid or shove a larger one off course. Such a method would be a last resort and carries its own uncertainties. Breaking a rock might create multiple dangerous fragments. Most experts prefer methods that keep the asteroid intact and simply redirect it. The goal is not to fight the cosmos with violence, but to nudge potential threats safely aside in a harmonious way. Planetary defense has become a global effort. No single nation can watch the entire sky, so astronomers worldwide share data and work together as Earth's sentinels. Space agencies collaborate on research and missions. The European Space Agency is sending a follow-up mission named Hera to study the aftermath of the DART impact on Dimorphos, examining the crater and how the asteroid reacted. This international cooperation underlines that protecting Earth is a unifying endeavor. The planet we defend is home to everyone we know, and a threat from space is a concern for all humanity. In this way, the challenge of cosmic hazards brings us together, erasing borders under a common sky. There is also a poetic side to this vigilance. By studying asteroids, we are communing with messengers from the dawn of the solar system. These rocks are ancient time capsules, holding clues about the formation of planets, and perhaps the origins of water and life on Earth. So our efforts to map and redirect asteroids also teach us about our own beginnings. In protecting Earth, we learn about the very materials that built it. In the long run, what once was a threat could become a promise. Future explorers may venture to asteroids not to deflect them, but to live and work on them. These wandering rocks are rich in metals, minerals, and ice. Someday, miners might gently land on an asteroid to extract water for drinking and fuel, or metals to build in space, turning what could have been a harbinger of destruction into a resource for creation. In that future, the line between defense and exploration blurs. The objects we guard against might become stepping stones to the stars. For now, we remain watchful and prepared. Each time we map a new asteroid or refine an orbit, the world becomes a bit safer. The night skies, once the realm of unknowable fate, have become a landscape we actively survey and manage. This newfound ability is a quiet triumph of our species, a sign that we have grown into planetary caretakers. We have learned the subtle art of cosmic stewardship, using knowledge and technology to shield our fragile oasis. It is a calm and steady confidence, knowing that as we venture outward, we are also keeping our home secure. In the grand story of exploration, this is a reassuring chapter, one where humanity steps up to protect the cradle that gave us life, ensuring we can continue our journey among the stars. As we safeguard our planet, we also gaze out at the stars and wonder, are we alone in this vast expanse? In the stillness of a clear night, as countless points of light sparkle above, it's almost impossible not to imagine life out there on some distant world. This age-old question has become a modern scientific quest. With sensitive instruments and careful listening, we have begun searching for any sign that we have cosmic company. One approach is to listen for signals among the stars. Not literal voices, but faint electromagnetic whispers that a distant civilization might send or leak into space. Since the mid-20th century, radio telescopes have been turned toward the sky in programs collectively known as SETI, the search for extraterrestrial intelligence. Night after night, giant dish antennas sit quietly, sipping the starry sky for unusual radio waves. They sort through natural cosmic static, the hiss of particles and the hum of stars, hoping to find a pattern or frequency that nature alone wouldn't make. This search requires patience and serenity. The stars do not reveal their secrets easily. In 1977, however, a brief excitement rippled through the SETI community. One summer night, a radio telescope in Ohio detected a strong, narrow-band signal that jumped out from the background noise. It lasted just a minute and then vanished. An astonished astronomer scribbled, "Wow!" next to the data printout, giving this mystery signal its famous name, the WOW signal. In the days and years that followed, countless attempts were made to find it again, but it never returned. While most scientists today suspect it was caused by a natural cosmic phenomenon, or perhaps some earthly interference, the WOW signal remains a tantalizing maybe, a gentle reminder that something unexpected could be out there. Today's searches have become more sophisticated. Arrays of radio telescopes scan huge swathes of the sky, and powerful computers sift through the data like someone searching for a faint melody in the wind. New projects funded by passionate visionaries are expanding the effort, listening not just for radio waves, but also looking for pulses of laser light or other technological traces. Every so often, there is a small stir, an odd signal, or a curious flicker of light. But so far, each has been traced to mundane sources or explained upon further observation. The cosmic silence continues, so the search goes on, quietly and optimistically. Meanwhile, another branch of the quest for life focuses not on intelligent signals, but on simple life forms thriving in alien environments. Our own solar system offers intriguing possibilities. Mars, our neighboring red world, has long captivated the imagination as a potential abode of life. Once, billions of years ago, Mars was warmer and wetter, with rivers and lakes. Today, it is cold and arid, but not completely dead. Robotic rovers are trundling across its dusty plains and ancient lake beds, searching for chemical clues and fossils of past microbes. They have found organic molecules in Martian soil and detected occasional whiffs of methane in the thin air, gases that on Earth can be produced by living organisms. These are not confirmations of life, but they hint that Mars had, and maybe still has, the right ingredients. Farther from the sun, icy moons guard liquid secrets beneath their frozen crusts. Jupiter's moon Europa is one such world. Its surface is a cracked shell of ice, and beneath it lies an ocean of liquid water, kept warm by the flexing pull of Jupiter's gravity. In that dark, hidden sea, might something swim or scuttle near thermal vents, as life does in Earth's deep oceans? We do not know yet, but future missions are being prepared to listen and look more closely. Europa Clipper, a spacecraft under development, will orbit Jupiter and make close passes by Europa, probing its ice for hints of the ocean's composition and perhaps detecting telltale chemicals that could indicate life below. Another ocean world, Saturn's tiny moon Enceladus, has already offered a direct taste of its secrets. In 2005, our Cassini probe observed geysers of water vapor and ice crystals shooting from Enceladus's south pole. Cassini daringly flew through those plumes and discovered organic molecules and even tiny grains of mineral that form in hot water. Those findings hint at hydrothermal vents on Enceladus's seafloor, the kind of environment where life on Earth may have first arisen. It is a tantalizing possibility that in the quiet depths of Enceladus's ocean, simple life forms might exist, utterly cut off from sunlight and slowly feeding on chemical energy from below. Not to be outdone, Saturn's largest moon Titan presents another intriguing, if exotic, possibility. Titan is shrouded in a golden haze of thick atmosphere. On its surface, rivers and lakes of liquid methane and ethane take the place of water. It's a frigid world, with a chemistry that runs on liquid hydrocarbons instead of H2O. Life as we know it would struggle there. But some scientists speculate about the chance for a completely different kind of life, using methane the way our life uses water. Titan's chemistry is rich in organic compounds. In its skies, complex molecules are formed in a slow dance of sunlight, nitrogen, and methane. NASA plans to send a drone-like probe named Dragonfly to Titan in the 2030s. It will hop across Titan's dunes and sample its chemistry, searching for any hints that Titan's strange environment has managed to spark its own form of life. Venus, our other neighbour, once considered inhospitable in the extreme, surprised scientists recently with a curious signal in its cloud decks. Amid the acidic clouds high above Venus's broiling surface, researchers reported finding phosphine gas, a molecule that, on Earth, is primarily associated with microbial life or human industry. Venus is an unlikely haven for life as we know it. Its surface is hot enough to melt lead, and its clouds are corrosive. But the detection of phosphine, if confirmed, suggests either unknown chemistry or the tantalizing possibility of microbes living in the temperate cloudy skies, floating as tiny airborne life. The debate over this finding continues, reminding us that the search for life can take us to even the unlikeliest places, and that we must keep an open yet skeptical mind. Beyond our solar system, the quest enters truly vast distances. Over the past few decades, astronomers have found a staggering variety of exoplanets orbiting distant suns. We now know of thousands of planets circling other stars, and the number grows every year. These alien worlds come in all sizes and conditions. Giant gas planets larger than Jupiter, small rocky ones, some baking close to their stars, others in gentle distant orbits. Among them are planets that, like Earth, reside in the habitable zone of their star, where temperatures could allow liquid water to exist. We have detected a handful of Earth-sized planets at the right distances from stars, not unlike our Sun. It's intoxicating to think that on some of these worlds, rain might fall, rivers might flow, and perhaps life might thrive under alien skies. However, finding a planet in the habitable zone is just the first step. The next challenge is to sniff out what's in those distant atmospheres. This is where the newest generation of telescopes comes into play. The James Webb Space Telescope, with its keen infrared eyes, has begun examining some exoplanets, detecting gases like water vapor, carbon dioxide, and methane in their air. In one recent case, the Webb telescope spotted signs of both methane and carbon dioxide around a planet about 120 light-years away. A hint that this planet could have an ocean and possibly even conditions for life. There was even tentative evidence of a molecule linked to life on Earth, stirring excitement among scientists. While far from proof of life, these findings mark the dawn of a new era where we can investigate worlds we cannot yet visit. Astronomers talk about searching for biosignatures, indicators that life might be present. These could be an unexpected abundance of oxygen in an atmosphere, perhaps paired with methane, since those gases together would normally react away unless something, like life, keeps replenishing them. Scientists also consider unusual colors on a planet's surface that might indicate vegetation, or the presence of odd chemicals that are hard to explain with geology alone. In the coming years and decades, new telescopes on Earth and in space will push these capabilities further. They will block out the glare of stars to directly image some exoplanets and analyze their light for traces of living processes. It's like detectives looking for fingerprints of biology on worlds so far away we see them only as tiny specks of shadow and light. And what if one day we do find something? Perhaps a clear signal in the radio noise that repeats and shows patterns, or a complex molecule unmistakably out of balance in an exoplanet's sky, or even microscopic fossils in a Mars rock. Any one of these would rank among the most profound discoveries in human history. One can imagine the scene. Perhaps a late night at a radio observatory when a distinct transmission is picked up that clearly originates from beyond Earth, or a future day when a rover on Mars sends back an image of a tiny fossil embedded in ancient rock. Such a moment might arrive quietly, as a line of data on a screen or a microscopic image in a lab. But its significance would echo across the world. It would mean we are not alone in a universe that suddenly feels a little less cold. Even finding simple microbes or strong evidence of past life beyond Earth would tell us that life is not a miracle confined to our world, but a natural phenomenon likely to sprout wherever conditions allow. In the absence of answers so far, we have made our own gentle attempts to reach out. In 1974, scientists used a giant radio dish in Puerto Rico to beam a simple pictorial message toward a distant star cluster. This interstellar greeting called the Arecibo message, contained information about our planet, our DNA, and our species, encoded in binary form, a cosmic introduction sent off to travel for 25,000 years to its target. We have also launched physical messages into the void. The Voyager 1 and 2 probes, which journeyed through the outer solar system, each carry a golden phonograph record. Etched onto these golden discs are sounds and images of Earth. Whales singing, children laughing, greetings in many languages, music from different cultures, the beating of a human heart. Voyager 1 has now entered interstellar space, the first human-made object to do so. It drifts in the quiet between the stars, carrying its greeting like a message in a bottle cast into a cosmic ocean. Perhaps eons from now, some distant intelligence will find it and know that we once existed, and that we too looked up and wondered. These efforts may never yield a reply, and that's all right. They symbolize something profoundly hopeful about us, a willingness to say hello into the darkness, with faith that someone, somewhere, might be listening. In return, we continue to listen as well. With each passing year, our instruments grow more sensitive, our surveys more comprehensive. We eavesdrop on the songs of stars and the whispers of galaxies, straining to hear even the faintest echo of another voice. It is a quiet vigil that requires both scientific rigor and childlike wonder. Whether the universe teems with life, or we are rare beings in a mostly empty sky, each discovery we make, a new planet in the habitable zone, an odd chemical on a distant world, a complex organic molecule in a Martian rock, brings us closer to understanding the tapestry of life. The search for alien life is, in many ways, a search for ourselves. It forces us to define what life is, to appreciate how special our own living world is, and to cherish the fragile biosphere we know. As we scan the heavens, we also reflect inward, grateful for our own existence. Under the quiet night sky, it's comforting to think that we may not be alone, that perhaps across the cosmic gulf, there are other minds gazing at their skies and asking the same questions. Until the day we learn the answer, if that day ever comes, the pursuit itself fills us with awe. It is a gentle quest, carried out in darkness with radio ears and optical eyes, bound by hope and curiosity. In this vast and ancient universe, the possibility of company, however distant, makes the cosmic ocean feel a little more like home. As we ponder the possibility of cosmic companions, we also look to our own future in the universe. Our dreams of exploration do not end with the planets of our sun. Beyond the edge of our solar system lie the stars, each a distant sun with its own family of worlds. For now, they are beyond our reach, separated from us by light years of empty space and immense time. But human imagination is not easily deterred by distance. Quietly, engineers and dreamers sketch out how we might one day cross those gulfs and become an interstellar species. The challenge is daunting. The nearest star system, Alpha Centauri, is over 4 light-years away, more than 40 trillion kilometers. With today's fastest spacecraft, it would take tens of thousands of years to get there. Rather than shrink from these numbers, we look for clever solutions to shorten the journey or endure its length. One idea is to build generation ships, vast spacecraft that are less like rockets and more like traveling miniature worlds. A generation ship would carry a whole community of people, perhaps hundreds or thousands, and everything needed to sustain them. Inside, there could be gardens and ponds, crops growing under artificial sunlight, and living quarters that feel like small neighborhoods. The ship would spin slowly to create a gentle illusion of gravity, so people on board could walk and live in comfort. Protected from cosmic radiation, with recycling systems endlessly renewing air and water, such a vessel could become a self-contained world for centuries. On a generation ship, no one person would see the mission from start to finish. The crew that sets out would grow old, and their children or grandchildren would continue the voyage. Generations would be born, live their lives and pass away, all while the ship inches across the stars. Imagine a child being born halfway through the journey, knowing no other sky than the star-speckled dome of the ship's interior ceiling. For her, the destination planet would be a place spoken of in stories, a promised land she might only reach in her old age, or that her own children might first set foot on. Maintaining purpose and hope over such long spans is as much a challenge as the engineering. The travellers would need a strong sense of mission and a rich cultural life aboard to give meaning to their years in transit. Perhaps they would celebrate milestones, when the ship reaches its midpoint, or when a distant target star finally becomes the brightest light in their sky. Every small victory would be cherished by a society voyaging through darkness. While generation ships represent patience and endurance, other concepts try to dramatically cut travel time by increasing speed. One avenue is advanced propulsion. Conventional rockets, which throw mass out their back for thrust, are too limited for interstellar distances. Scientists are experimenting with more efficient methods, like ion drives that gently accelerate a craft for months or years, reaching higher speeds than chemical rockets can. Ion engines have already propelled probes to asteroids and beyond, their faint blue glow a promise of the future. But for the stars, we envision bolder ideas. Nuclear rockets powered by splitting or fusing atoms, antimatter engines using the explosive energy of matter-antimatter annihilation, or even engines that ride on the fabric of space itself. One promising near-term idea is to use light, specifically light sails. A light sail is a thin, mirror-like sheet that can catch photons the way a boat's sail catches the wind. Though light has no mass, it carries momentum. With a powerful laser beam or the sun's own rays, a spacecraft with a wide sail could gradually accelerate. A project called Breakthrough Starshot has proposed sending swarms of tiny gram-scale probes attached to sails. Enormous lasers on Earth would shoot intense beams at them, pushing them to perhaps 20% of light speed. At such speeds, these microprobes could reach Alpha Centauri in just 20 or 30 years. They would be too small for humans to ride, but they could send back pictures and data, our first virtual explorers to another star. For crewed ships, scaling up that concept is much harder, but perhaps a future civilization could build laser launch systems in space. Another idea is nuclear fusion propulsion. Fusion, the process that powers the sun, could theoretically propel a vessel at a significant fraction of light speed if we could build a reactor that runs continuously and safely. Decades ago, visionary engineers designed a concept called Project Daedalus, a huge uncrewed starship that would detonate small fusion pellets to push itself forward, potentially reaching a nearby star in a century or two. Today, fusion power is still experimental on Earth, but if humanity masters it, the stars might become more accessible. Then there are concepts that border on science fiction, but are grounded in real physics equations. Ideas like warp drives and wormholes. A warp drive, as theorized by physicists, would involve bending space around a vessel, contracting space in front of it and expanding it behind, effectively moving space itself rather than the ship. If it were possible, it could allow faster-than-light journeys without technically breaking the cosmic speed limit, because locally, the ship wouldn't be moving faster than light. However, the energy requirements predicted by theory are enormous, and it calls for forms of matter we're not even sure exist. For now, warp drive remains a dream, a placeholder for some future breakthrough in understanding gravity or quantum physics. Wormholes, hypothetical tunnels through spacetime connecting two distant points, are another tantalizing idea. Perhaps they occur naturally or can be created by advanced beings, providing a shortcut between stars or even galaxies. Yet, like warp concepts, wormholes so far live in the realm of speculation and mathematics. None have been observed or built. They remain hypothetical. Still, it's a gentle comfort to imagine that the universe might allow such shortcuts, even if they're beyond our grasp at present. In the meantime, the first steps toward interstellar travel may be far more modest. We might begin by establishing bases and colonies on worlds closer to home, stepping stones into the cosmos. A small habitat on the moon could be humanity's first outpost beyond Earth. One day, astronauts might live for months at a lunar base nestled near the moon's south pole, where the sun's rays provide continuous power and deep craters hide deposits of ancient ice. In the airless silence of the moon, they would work in pressurized modules, growing plants in lunar soil, extracting water from ice to drink and to make rocket fuel, and building structures with moon dust and 3D printers. Outside their habitat, the sky is black, even at noon, and Earth hangs above the horizon, a blue marble rising and setting, a constant reminder of home. Life on the moon would be harsh, but exhilarating, teaching us how to thrive on a world with no atmosphere and weaker gravity. Each success on the moon becomes a lesson for venturing further. Mars, the red planet, beckons as the next giant leap. In the thin, cold air of Mars, future pioneers might raise habitats and greenhouses, turning barren soil into gardens under domed enclosures. They would wear protective suits to walk outside, their footprints joining the tracks of rovers in the rust-colored dust. Over time, a village could grow in a sheltered Martian valley, clusters of habitats connected by tunnels to keep out the choking dust and radiation. At dawn, settlers might look up to see the sun rise, a smaller, dimmer sun than on Earth, painting the pinkish sky. By night, they would watch two tiny moons, Phobos and Deimos, drifting overhead like swift stars. In this quiet frontier, humans would learn to live with limited water and to generate oxygen, perhaps by extracting it from Martian ice or air. They would rely on one another in an environment where stepping outside is always dangerous without the right gear. The first footprints on Mars will one day be joined by permanent boots on the ground, a testament to human tenacity. A Mars settlement would also be a profound milestone. We will have become a multi-planet species. That achievement would ensure that even if one world faces catastrophe, human life could continue on another. We can imagine futuristic habitats that are neither on a planet nor a traditional ship. Enormous rotating colonies in space, sometimes called O'Neill cylinders. These would be like artificial worlds, spinning tubes miles long where centrifugal force mimics gravity on the inner surface. Inside, whole landscapes could be built. Towns, forests, lakes, under an arched sky of metal and glass, with sunlight redirected inside by mirrors. Residents could enjoy day and night cycles. Such colonies might initially orbit our sun, but one day they too could journey to other stars, turning the concept of a spacecraft into something more like a moving city. Through all these ideas runs a common thread: the resilience and adaptability of life. Just as life spread to fill every niche on Earth, from deep ocean vents to mountaintops, so might human life one day spread beyond Earth's confines to habitats as varied as starships and other planets. The people of the far future may look up at a sky from the surface of Mars, or from inside a rotating colony, or from the observation deck of a ship between stars, and they will see the constellations from a new vantage. Perhaps they will tell stories of old Earth as a distant, mythic homeland, even as they create new homes among the stars. These prospects unfold over centuries and millennia, a slow, steady migration outward that exceeds a single lifetime. Yet we have already begun in small ways. We have flung probes like Voyagers into interstellar space, sent orbiters and rovers to other planets, and even now our scientists and visionaries plot the trajectories of ships that might sail when our grandchildren are grown. Each mission and each new technology is like laying a plank on a very long bridge to the future. Standing at the brink of this future is both humbling and exciting. The stars have beckoned to us since we first saw them, and to walk among them would be a poetic fulfillment of a journey that began when the first humans looked up in wonder. It may take generations, but little by little we turn what once was pure fantasy into actionable plans. In doing so, we carry forward that quiet, mysterious drive to explore that has always defined us. Someday, an engine will ignite in the darkness, and a ship unlike any built before will depart the solar system, carrying explorers bound for a planet orbiting a distant sun. On that day, humanity will become an interstellar traveler in earnest. And even then, under alien constellations, we will remember our small blue origin and the long road we traveled to reach it. The future of space exploration is truly limitless. It stretches out into the unknown, inviting us onward with a silent, irresistible allure. In the cosmic ocean, we will navigate not just with technology, but with hope and the steady light of curiosity guiding our way. Yet, for all the progress we have made in understanding the cosmos, profound mysteries remain. In fact, the more we learn, the more we realize how much is unknown. One of the greatest puzzles is something we call dark matter. When astronomers look at galaxies, they see stars rotating and clusters of galaxies moving in ways that cannot be explained by the gravity of visible matter alone. It's as if an invisible mass is present, pulling on everything with its gravity. This dark matter neither emits nor absorbs light, so we cannot see it directly. We only infer its existence from its gentle gravitational tug on visible stars and galaxies. Astonishingly, calculations suggest that this unseen matter outweighs the ordinary matter, stars, gas, planets, and dust, by a factor of 5. In other words, most of the matter in the universe is invisible and mysterious. We don't yet know what dark matter is made of. It could be some new kind of subatomic particle that eludes our detectors, silently swarming through and around galaxies. Scientists around the world are searching for clues, placing detectors deep underground and launching observatories into space, hoping for even a tiny glimpse of these shadowy particles. The idea that the vast majority of matter is hidden from our view is humbling. It reminds us that we have uncovered only a small fraction of nature's full inventory. And then there is an even stranger discovery: dark energy. In the late 20th century, astronomers expected that the expansion of the universe, set in motion by the Big Bang, should be slowing down over time, as gravity pulled matter back together. Instead, to their surprise, they found that the expansion is speeding up. Distant supernovae, exploding stars used as markers, appeared dimmer and farther away than anticipated, indicating that something is pushing the universe outward, faster and faster. This unknown force was dubbed dark energy. It seems to permeate all of space like a subtle pressure or tension that counteracts gravity on the largest scales. According to current estimates, dark energy constitutes about 70% of the total energy content of the cosmos. We find ourselves in a universe where the vast majority is invisible and enigmatic. Roughly 95% of the cosmos is made of dark matter and dark energy, entities we barely understand. Only about 5% is normal matter that forms stars, planets, and people. So we are like swimmers at the surface of a deep, dark ocean, aware that much lies beneath that we cannot yet see. Investigating dark energy is challenging because it is diffuse and reveals itself only over immense expanses of space and time. Nonetheless, researchers continue to study it by observing the universe's expansion history and the large-scale distribution of galaxies. They also hope that future breakthroughs in physics might illuminate its nature. These mysteries don't disappoint us. They inspire wonder. Knowing that so much remains to be discovered means the cosmic story is far from fully told. We stand like explorers on a shoreline with a vast, unexplored ocean of truth stretching out before us. Each new telescope and experiment is like a ship setting sail into that unknown, seeking insights into dark matter, dark energy, and other puzzles. Another fundamental mystery lies in the realm of extremes, black holes, and the very beginning of time. We know black holes are places where matter is crushed so densely that not even light can escape. They teach us about gravity at its most intense. But at the heart of a black hole, our current physics breaks down. A singularity, a point of almost infinite density, defies understanding. Similarly, if we wind back the cosmic clock to the moment of the Big Bang, the universe was once incredibly hot and dense. Understanding those first moments requires melding our theories of the very small, quantum physics, with our theories of the very large, general relativity. Right now, those two great frameworks of physics don't perfectly agree on what should happen at such extremes. Scientists dream of a unified theory, often called quantum gravity, that would describe the fabric of space-time on the smallest scales and reveal what happens inside black holes or how the universe was born. Achieving that would answer some of our deepest questions. How did the universe begin? What is time, really, and how does it weave together with space? It might even open doors to concepts we can scarcely imagine now, perhaps new ways to manipulate gravity or travel via cosmic shortcuts. Ideas that remain speculative but captivating. There are also questions about life and consciousness that border on the philosophical. We still do not know how inanimate matter sparks into life, or how consciousness arises from the brain. These too are part of the grand cosmic mystery because they ask what role life plays in the universe. Are we an accident or an inevitable outcome when conditions are right? As we wander among the stars, looking for other living worlds, we are also trying to understand the miracle of life itself. Every rover that searches for fossils on Mars, or probe that samples the oceans of an icy moon, is, in a sense, asking, how does the universe make life, and how often? Facing these unknowns might make us feel small, but there is also a sense of excitement. The unknown means there are endless possibilities for discovery. It ensures that science will continue, that future generations will have plenty to explore and understand. In a way, the universe maintains its aura of mystery, no matter how far we come. Each answer leads to new questions. That is a beautiful thing, because it means the well of wonder will never run dry. We can look up at the night sky, as people have for millennia, and still be greeted by questions as vast as the sky itself. The darkness between the stars isn't empty. It's filled with secrets, waiting patiently for curious minds. In confronting these cosmic mysteries, we are reminded of the spirit of exploration that has carried us this far. Just as our ancestors crossed oceans without knowing what lay beyond the horizon, we peer into the cosmic dark, propelled by curiosity and a quiet faith that knowledge is attainable. Each puzzle solved will enrich our understanding of existence and perhaps reveal new wonders we can't yet imagine. The universe, with its dark matter, dark energy, and unfathomable origins, invites us to keep searching. In that pursuit, we find not only answers about the cosmos, but also deeper meaning about our own journey within it. After journeying through these mysteries and wonders, we find that all our exploration of space ultimately leads us back to ourselves, illuminated by a new light. All our voyages outward have prompted introspection. The universe has a way of humbling us, showing that our daily worries are small against a backdrop of galaxies and eons. Yet, knowing the grandeur of the cosmos can be oddly comforting. We realize that we are part of something immense and ancient, that we're woven into the very fabric of this universe. In a literal sense, the iron in our blood and the calcium in our bones were forged in stars that died long before Earth was born. We are children of the cosmos, made of its very substance. This connection brings a profound sense of belonging, as if the universe is not a cold foreign place, but our extended home. Many astronauts have described a life-changing experience when seeing Earth from space, often called the overview effect. High above, looking down on our planet, they see a fragile, luminous sphere suspended in darkness. The thin atmosphere glows softly, hugging the Earth like a delicate veil. From that vantage, there are no borders, no divisions, just one world with ocean swirls and land masses, clouds drifting over continents. The famous Earthrise photograph taken from lunar orbit, showing our blue planet emerging above the moon's grey horizon, moved millions by revealing Earth as a small, radiant globe in the dark of space. Images like this, and the experience of astronauts, highlight how our conflicts and differences melt away when viewed against the vastness of space. What stands out is how interconnected and precious all life on that tiny world is. Those who return from space often feel a deep responsibility to protect our planet, and a calm understanding that we all share this one home. The overview effect is essentially a reminder of unity, a perspective that we are one human family, adrift together on a small rock in the cosmic sea. Space discoveries and images have a way of stirring our deepest emotions. Think of the famous photograph of Earth taken by Voyager 1 from billions of miles away, the pale blue dot image. In that photo, Earth is nothing more than a faint pinprick of light caught in a sunbeam, almost lost in the immensity of space. On that speck is everyone you know, every human who has ever lived, every dream, every love, every bit of our history. Reflecting on this can be strangely soothing. It puts things in perspective. Our quarrels, our achievements, our worries, all play out on a mote of dust suspended in a sunbeam. And yet that mote of dust is home. It's the only haven for life that we know of, and that makes it infinitely precious. The pale blue dot image teaches us both humility and gratitude. This shift in perspective is one chapter in a long story of revelation. Not so long ago, we believed Earth was the center of the universe. It was comforting to imagine everything revolving around us. But then came the realization that Earth is a planet orbiting the Sun. Later we learned that our Sun is just one star among hundreds of billions in the Milky Way galaxy. And the Milky Way itself is only one of countless galaxies scattered through space. Each of these revelations made humanity a bit less central in the cosmic scheme, yet each expanded our understanding immensely. Instead of a small, cozy universe built just for us, we found a vast, complex cosmos in which we are a part. We lost our privileged physical position, but we gained a more awe-inspiring reality. We went from living in a little dome around which everything turned, to living in an expansive universe full of galaxies, star nurseries, nebula, and mysteries. Realizing we are not the physical center of creation has been humbling, but also liberating. It allowed our curiosity to roam beyond ancient boundaries. Our place in time has also been redefined in astonishing ways. The universe is around 13.8 billion years old, a time span difficult to grasp. A useful metaphor is the cosmic calendar. Imagine compressing the entire history of the universe into a single calendar year, with the Big Bang on January 1st and the present moment at the end of December 31st. In this view, each month would represent a little over 1 billion years. Our Milky Way galaxy forms around March. The Sun and Earth appear roughly in early September. Life on Earth begins soon after, simple cells emerging in the young oceans. Through October and November of this cosmic year, life slowly evolves, becoming more complex. Dinosaurs roam around December 25th and meet their end on December 30th. The first early humans appear on the evening of December 31st, and all of recorded human history, every pyramid built, every painting made, every book written, every journey taken, occurs in the final minute of the final hour of December 31st. In that last minute, we developed agriculture, cities, science, and spaceflight. It's mind-bending. We are so new in the universe, a species born in its final cosmic minute. Yet look how far we've come in that brief moment, and think of how much future may lie ahead if we take care of our world and continue to explore. Humanity's story is only beginning when set against the scale of the cosmos. In taking these mental journeys across billions of light years of space and billions of years of time, we come to see ourselves both as tiny and as significant. Tiny, because physically we occupy such a small corner of the cosmos and such a fleeting moment of its history. Significant, because we are a part of this cosmos that can reflect on itself. Through us, the universe has gained eyes and ears, hands and minds. Our exploration, our science, our art. These are the cosmos experiencing itself in myriad ways. It's a beautiful idea that by learning about distant planets and stars, we are also learning about ourselves. As the astronomer Carl Sagan put it, we are a way for the cosmos to know itself. Our quest for knowledge is the universe's way of reflecting on its wonders. When we realize this, it can bring a deep sense of peace. We are not outsiders to the universe. We are an expression of it, like a wave rising from a great ocean. When the wave subsides, it returns to the ocean. Likewise, Each of us eventually returns to the universe's cycle of matter and energy. Knowing this fosters a gentle reverence for life and the world. We belong here. We always have, and always will, at the fundamental level of atoms and stardust, dancing in an endless cosmic cycle. The mystery of whether we are alone in the universe is as much a philosophical question as a scientific one. If it turns out that life is exceedingly rare, that perhaps we are one of the very few, or even the only spark of consciousness in our galaxy, then all the more precious is this flame on our pale blue dot. Then the duty to cherish and preserve life becomes even greater, a responsibility we should not take lightly. If instead the cosmos is filled with life and other intelligences, then we are part of a much larger community of beings. That possibility can fill us with hope and excitement, imagining the stories and knowledge other beings might share. In both scenarios, our longing to know and to connect is what drives us. The search and the wonder behind it bind us to the universe. The very act of exploration answers a deep call within us. From early seafarers crossing uncharted oceans to modern astronauts launching beyond the sky, the urge to see what lies beyond is ingrained in our nature. Some might ask, why venture to worlds so far away when we have problems to solve at home? The gentle answer lies in curiosity and the need for inspiration. Discovering the unknown transforms us. Each new insight, seeing the craters of Pluto up close, or finding evidence of water on Mars, ignites a spark of wonder, not just in scientists, but in people everywhere. It reminds us that there is more to life than the routines of our days, that the universe is vast and filled with marvels. We are explorers by birthright, and this endless frontier nourishes our spirit. Such discoveries can inspire the next generation of thinkers and dreamers, and they can unite nations in common pursuit. The International Space Station, for example, is a beacon of cooperation, former rivals working together, living side by side in orbit, exemplifying what humanity can achieve when we focus on exploration and knowledge. There is also a philosophical lesson in how we push into space. It teaches us about our limits and how to transcend them. We face the void with technology and teamwork, but also with imagination and courage. Each mission that succeeds, a rover surviving a perilous descent to Mars, or a probe soft landing on a comet, shows that things once thought impossible can become reality through patience and ingenuity. This mindset spills into how we tackle challenges on Earth. The belief that we can solve difficult problems, that we can venture into the unknown and return with wisdom. In a universe that offers no manual, our willingness to seek and learn is what creates meaning. Some find in the cosmos a profound spiritual or poetic resonance. Gazing up at a clear night sky full of stars can feel like standing in a great cathedral, silent and filled with ancient light. It can stir feelings of awe and reverence. Whether one interprets that in religious terms, or simply as a deep emotional response, the effect is similar. We feel connected to something far larger than ourselves. The awareness of our planet as a tiny blue oasis adrift in a vast darkness can prompt a sense of unity and compassion. We see that all people and all life are together on this one fragile world. In that way, exploring the cosmos teaches us to be better stewards of each other and our planet. As our journey through these space facts and discoveries comes to a close, we find ourselves filled with a quiet awe. Over the past hours, we've travelled in our imagination from the surface of our planet to the edges of the observable universe, and even into the far future of what might be. We've pondered black holes and distant galaxies, stood on the shores of alien moons in our mind's eye, and envisioned the fate of life and intelligence in the cosmos. It's a lot to take in, yet a calming thread runs through it all. The universe is vast beyond measure, but here we are, small creatures with big curiosity, able to appreciate its grandeur. In the stillness of this moment, under whatever sky arches above you, you might sense a gentle connection to the cosmos. The same stars we've been speaking of are perhaps glittering overhead where you are, or will be later when night falls. They cast their ancient light down on us, a reminder of the enduring continuum of time and space in which we exist. Take comfort in that continuity. Long before we were born, the stars were shining, and long after we are gone, they will continue to shine. Our lives, as fleeting as they are part of this great cosmic story. The discoveries and wonders we've shared are more than just information. They are invitations to ponder and to dream. They encourage us to explore, not only in space, but in our own lives, to face challenges with courage, to see the bigger picture when life feels overwhelming, and to find beauty in the unknown. In a way, learning about the cosmos is like having a calm conversation with eternity, one that can put our mind at ease. Now, as we conclude this cosmic voyage, imagine yourself floating gently among the stars, weightless and tranquil. All the knowledge and imagery we've journeyed through swirl softly in your mind like stardust. The universe holds many secrets yet, but there is no rush. We will continue exploring, slowly and steadily, as we always have. In the meantime, we can simply appreciate the wonder of existence. Allow the vastness and mystery of space to lull you into a peaceful state. As you breathe softly, feel your body relax, as if you too are floating among the stars, safe and serene. Know that you are part of something vast and magnificent. Above you, the stars watch in silence, as they have for billions of years. Our story, the human story, is one tiny thread in the cosmic tapestry, but it is our thread, and it is precious. As a final thought, consider the night sky one more time. A dome of deep, velvety darkness, sprinkled with the light of distant suns. It's a view that has comforted and fascinated every generation before us. We continue that tradition, gazing up, wondering, learning, and finding peace in the knowledge that the cosmos is our home. May the calm and mystery of the stars accompany you now into restful sleep, and may the awe of what lies beyond carry on in your dreams. Safe journey, fellow traveller, and good night.